Dear colleagues, thank you very much for being here. Already after 3 days is a lot. I'm very happy to receive, as you can see, and if you have seen the program, I'm not Ernesto Lievana, I'm Beatriz Guerra. I am EFSA lead expert for molecular epidemiology and senior scientific officer at the BioHow unit, and I work on resistance already since more than 30 years. So it's a pleasure for me to be here. Apologies from Ernesto, who is at home and could really not connect today. And I have the pleasure to present and introduce and moderate this session. The idea for the session came because last year we published a scientific opinion on the role of the food-producing environment on antimicrobial resistance. Because everybody is doing a lot of things on the environment. We think on the One Health concept and environment is missing, but what was related more to EFSA is what is the food-producing environment, not the general environment. It was an opinion where we work very close with all the sister agencies, with ECDC, with EMA, with the environmental agency, and together we put this session. From the point of view, we have identified many issues in that opinion, many things that we didn't know how are going to impact AMR. We know that there are many challenges and changes in the next years in the agri-food sector or climate change, and many things that we don't know. So we decided to put this session having many talks in comparison to others, very short ones, but all of them tackle important points that we saw in this scientific opinion. So we will have a first subsection that we put this in, what is important from the public health point of view, what is important from the environment point of view. Then we will see some of these challenges and changes that are related to the climate change, to other agri-food changes, use of antimicrobial, and use of, for example, reclaimed water. And then in the last subsection, in the third subsection, we will see things that can be done to be prepared, like it could be surveillance, it could be according to the changes in the regulations, or it could also be research. At the end, we will have a plenary discussion where we will have all the chairs and all the speakers. Unfortunately, you know that we have suffered COVID and strikes all this week, so many of the speakers and 2 of the chairs will be online. We have 4 speakers in the room and the rest of the chairs. And then I really ask from the very beginning a big applause for my rapporteurs that have worked like crazy to prepare this. So with this, I give the talk to the floor to the first chair, that is Dominique Monet from the European Center of Disease Control from the ECDC, and he is the head of the Antimicrobial Resistance and Healthcare Associated Disease unit or section. Infections. And Dominique will share this, and I will support him with some of the questions. So thank you very much. The floor is yours, Dominique.
Thank you very much, Beatrice. Yes, the ECDC is the European Center for Disease Prevention and Control. And we make sure to always use this word prevention. But thank you. So we have 2 speakers for this first session that will focus on the public health aspects of antimicrobial resistance, but again in a One Health perspective, because this is the theme of the conference. And our first speaker is Dr. Robert Skov from Statens Serum Institute in Copenhagen, Denmark. Dr. Skov is heading the International Center for Antimicrobial Resistance Solutions, and he insists on the word solutions. The center is called ICARS. The goal is to focus on low and middle income countries to provide evidence for tools that would actually put the national action plans into action. Robert Skov is a public health microbiologist with an interest and experience with animal and human health interface, and he's also a member of the AMEG panel at the EMA. Dr. Skov.
Thank you very much, Dominic. Thank you, Beatrice, for this kind introduction. It's a great pleasure to be here today, and I will try to give you a short glimpse of the public health issues with antibiotic resistance, where we are looking more on the cross-border and cross-sector problems. So very many of you have most definitely seen these data that just recently came out in the Lancet Infectious Disease. It's a Graham study, which reported that almost 5 million deaths were associated with drug resistance in bacteria in 2019. One has to be a bit careful with that number there, because the easier is that you have found resistant bacteria and people are died, but it's not a causal relationship. But on 1.3 million of these cases, there was actually, it was estimated that the death was directly related to the antimicrobial resistant bacteria. And just to put that in perspective to COVID, right now, I believe that we are in worldwide approximately 6.6 or 6.5 million deaths. This year is only in 2019, and the number is only increasing. So it really is, we are in the middle of the next pandemic already now, even though that very few talks about it. 1.3 million deaths, that is almost the same number as what is dying from HIV and malaria combined. And it is projected, if nothing is done, then in 2050, 10 million AMR deaths can be 10 million deaths can be related to AMR. This is very skewed, because 9 million of those, 90%, is actually in low and middle income countries. But as I will come back to you, this has very big relevance for us as well. Not only is it causing a lot of morbidity and mortality, but also cost-wise. The World Bank estimated in their first report that this year could end up in an extra cost of between 400 million and $1,000 billion in 2050. So we are talking massive amount of money if we don't curb this. As you also can see, this year is affecting Southeast Asia and Africa the most, but also in Europe, it is a significant problem. So when we're talking about antimicrobial resistance, well, for most of you here, this year is really common knowledge, but I think it's really worth reiterating. AMR is a full natural phenomenon that actually allows microorganisms to survive. So it's a kind of their survival mechanism. And some of the bacteria is born with it, and some are acquiring the resistance because there is a selection pressure that promotes that. But what should be very clear is that in all bacterial communities, both in man, human agricultural environment, there is antimicrobial resistance both in pathogens and in non-pathogenic, or what we call commensal bacteria. Furthermore, these resistance genes can be placed on mobile genetic elements that easily transport themselves from one bacteria species to another, and thereby spreading the resistance horizontally. There can also be other genes on these elements, which means that there can be co-selection by non-antibiotic compounds, for instance, heavy metals. Exchange of resistant genes and antibiotic resistance do not respect neither borders nor sectors. And this means that we really need to see it in a one health, one world perspective, which I also will allude a bit to. What about antimicrobials in this phase here? Well, antimicrobials speed up both the de novo creation, what is often mutations, as well as the uptake of antibiotic-resistant genes. It furthermore kills the sensitive bacteria of your normal flora, really giving space to the resistant bacteria to grow and proliferate. And that means that the spread of resistance is not heavily affected, both of the use of antimicrobials, but also, of course, on the transmission of these bacteria. And transmission routes should not be forget in this sense here, neither should things to mitigate it, but I'll come back to that at the very end. The ecology of resistance, as you can see in this picture here, is massively complex. And what is easily seen is that there is interconnections with all the different sectors. And this means that we actually are looking into the One Health, where we see One Health as an integrated, unifying approach that aims to sustainability, balance, and optimize the health of people, animals, and ecosystems. And then it carries on in a bit more elaborate here. But I think this year is really important to remember that even though resistance in humans mainly are created by the antibiotics used in humans, there is an extra part coming also from non-human parts. Not only do we have to look at this in a One Health perspective, human live animals, goods are traveling all over the world. This picture here shows you, shows you the travel routes of humans, how it is. And if you do the same thing for goods, you will see similar pictures. And this means that we can not only look at this on a One Health perspective, but it's actually a One Planet perspective that we have to look at it. And this is, again, coming back to what I started with. We saw lots of resistance, lots of problems in LMICs. Where do we travel to? Where do people come from? Where do we travel with goods? Very much between Europe and other different continents in the world. When we're looking into the intersection, because this is what is the key here, then we have to see a bit about the usage of antibiotics, given that this is the highest selecting factor at all. And in fact, over 70% of all antibiotics is used in food-producing animals. This is very varied. So as below 5 milligram per 5 milligram per kilo animal produced in countries like Norway and Iceland, up to more than 300 milligrams per PCU in China and Cyprus. You see here a huge difference, but and this amounts actually to an estimated total sum of 130,000 tons, which was used globally in 2013. What is really scary is that this is projected to increase by 50% in 2030. Furthermore, in 2019, antibiotics were used for growth promotion, not treatment, simply growth of animals in 26% of the countries worldwide. We don't do it in EU, but this year again, we are one world. And finally, illustrating this with the one world, resistant bacteria where more that have resistant genes that is resistant to more than 50% of the tested antibiotics, that increased with more than 160% between 2000 and 2018 in both pigs and chickens. The chickens I will come back to in a second. In humans, on the other hand, because we have to remember the human consumption, there it is very diverse. In high-income countries, the use in DDDs per 1,000 inhabitants increased only slowly or even declined from 2000 to 2015. Whereas again, Going back to the LMICs, which is hardest hit, there was a significant increases, especially in the WHO watch group of antibiotics. And we have to remember that use in humans keep the selection pressure on resistant genes, regardless where these are created. Here you see the levels of resistance in some selected bacteria. This year is bloodstream infections, where from 2013 and 2020 for 5 different bacteria, and you see the legend here at your right. Oops, sorry. Here, out here. And what you can see here is that for MRSA, we actually see a slight decrease. And remember, this year is only in a 7-year time span. VRE and E. coli, almost the same level. But for Klebsiella pneumonia and for multi-resistant Acinetobacter, we see a clear increase. And you also see a clear south-north difference, and sometimes also an east-west difference. Why did I show you these bacteria? Well, because as Beatrice started to mention, in the scientific opinion made by EFSA here in 2021, the biohazard panel identified a number of bacteria where the resistance was of high priority of public health. There's the 2 top one, which is the known zoonotic bacteria, the Salmonellas and the Campylobacters, resistant to either third-generation cephalosporins and carbapenemases. I don't want to mention all of them. This is going to be boring then. Campylobacter to macrolides and fluoroquinolones, but also some of the non-traditional zoonotic bacteria, or wouldn't even call them normally zoonotic. The Enterobacterialis, the E. coli, Klebsiella pneumonia, the Staphylococcus, which was for many, many years a pure human problem, but changed with the livestock MRSA. The VRE, which is a problem, but actually with a very little overlap between humans and animals. And then the Acinetobacter baumannii. If you see, those here were those that I showed you just before. So what are the contributions from resistance from the food-producing animal chain or environment? Well, as it was clearly pointed out in the scientific opinion, this is very difficult to answer precisely. And one of the most clearly thing is that we find both the resistant bacteria, similar genes, in all sectors, meaning both in humans, in food-producing animals, in humans, and in the environment. But actually linking that to a direct transmission has been almost impossible, I would say. But you need to know, and remember a bit of what I said before, transmission of resistance is not necessarily linear. You can either have that it transmit you and give directly disease, that's the easy part. But in very many cases, it transmits where you get carriage in your gut, carriage on your skin, and then you pass it on to a new person. And then this person either gets sick or passes it on, but still it came from perhaps an animal there. Furthermore, the resistant genes can, by with transfer, go from one species to another, all making it very difficult to prove the links. That said, we have just been, or Lance Price, which you can see cited here, has just looked at some data from US where they have been looking at the E. coli, and what they have done there is that they have taken E. coli for human urinary tract infections. And in the E. coli, they have looked for poultry markers, and in 8% of the human infections, urinary tract infections, they found clear poultry markers in the E. coli, meaning that these strains very recently was in these animals here. 8%, that's not much. Well, it's actually about 500,000 cases in US. And this is in a country where we have fairly high standards of hygiene and biosecurity. try to translate this in your mind to a place with low level of biosecurity here. Furthermore, 8% or 500,000, this is more than any other non-E. coli uropathogen in US. So there seems to be some kind of link here. So in conclusions, AMR is sadly, I would say, a silent evolving pandemic. What do I mean by this? Well, how many of you before the Graham study was aware that this cost actually more than 1 million direct cost of death per year? This is an enormous number which just will continue and continue. And this is to a large extent unrecognized both by the civil society, the policymakers, and the politicians. There is an urgent need for actions in all sectors. These actions need to be both in each of the sectors, but certainly also cross-sectorial. But then we need to have the policymakers and the politicians to make policies and structures which ensure cross-sector mitigation of AMR, which is sadly really missing. Those have to be both locally, regionally, and globally. Prudent use of antimicrobials and co-selecting agents in all sectors, antimicrobial and diagnostic stewardship, meaning that we need new diagnostics that is rapid, user-near, affordable. We really need innovation. And we need innovation of non-antimicrobial treatment modalities. And finally, what I started to say, don't forget the mitigation of transmission of antimicrobial resistant bacteria and genes, meaning simple good hygienic measures, biosecurity, and not the least also in animals, good management practices. So at the end, I was asked to put 2 words which could be in a word cloud, and the 2 word or sentences I chose was silent evolving pandemic and One Health. And I want to acknowledge my good friend Lance Price, professor at George Washington University, for those E. coli data, and thank you for your attention.
Thank you very much for setting the stage so nicely. Now we understand why it's so important for us humans. We have a second speaker for this session, Professor Luisa Peixe. She's a professor of bacteriology at the University of Porto, Portugal, with a long-term research interest in One Health and the links between animals and humans. She's also a member of the Biohazard panel of EFSA, and she will now present the other side of a coin, that is antimicrobial resistance in food-producing environment. Please.
So many thanks also for the organization of this event, for inviting me. And I will take I will take also the presentation that we had from Robert for this presentation, because it really was important, the information that he already brings. And just to remind you that, in fact, as a consequence of the high amount of antibiotics that are used in the animals and humans, these are the hotspots for emergency and spread of an antimicrobial resistance, and this spread could occur by direct contact throughout food or through the environment. And the environment, although in the last years, as an increasing recognized importance, the food production environment is not so well studied and not also so well known about this really importance. This need for further scientific understanding of food-producing environments, contribution for the emergency and spread of antimicrobial resistance was also recognized by the European Commission on the AMR action plans. And based on this information, the biohazard panel of EFSA undertook a self-mandate with this with this purpose of assessing the role played by the environment in the emergency and spread of antimicrobial resistance through the food chain. And as Beatrice already mentioned, this was all done with the consultation of other European agencies. And here I will just summarize the information that we gathered in this opinion that is publicly available. The terms of reference that we had for revising scientific evidences addressing this topic, the first of those terms of reference was to identify the main sources and transmissions routes of AMR leading to contamination of foods of animal and non-animal origin, also to identify among those AMR threats, to identify the ones of highest priority, and for those also to identify what are the risk factors that can influence their occurrence and persistency in the food-producing environment as well as in foods. Also, we are asked to evaluate and the mitigations that exist and also the impact of those mitigations. And the other also request that we had was to evaluate the data gaps and also to also propose recommendations for future research activities in the European area. The sectors that were included in this mandate were the plant-based food production sector, as well as terrestrial animals, here considering poultry, also cattle and pigs, and also the aquaculture settings. This work was conducted, as I mentioned already, by a set of experts led by the biohazard panel. And from the information gathered, what you can see here is an overall overview of the different information that was gathered. And this, in fact, the first overall view that we have reveal what Rob already mentioned, that there is a link between the different settings, and also there is a link between the food-producing sectors and the human, animal, and environmental sources of antimicrobial resistances, genes, and bacteria. And this is in a cyclical manner. You can see that in this left side of this scheme, there are a summary of the sources, food environmental sources, so that we identified during this study. And it was possible on all those sources associated to food-producing environment to observe the presence of antibiotic-resistant bacteria and antibiotic-resistance genes. Also, in all sectors, we are able to see the presence of these bacteria. And the most important source that was identified was the fecal waste, and that means that it can be of human and animal origin, with obvious impact on the plant production as well in aquaculture. Regarding other sources for terrestrial animals, it was quite difficult to rank in terms of importance due to the lack of data, with some circumstantial evidences pointing for feed and workers as an important source, but for the aquaculture, besides this water that could be contaminated with fecal matter, was also identified in the report that we had accessed, that feed and sediments associated with the movement of water, with the presence of water, were also important in aquaculture. Several of the highest priority antibiotic-resistant bacteria and the resistance genes that Robert Skov already talked about were really also observed on the reports that are available. And here you can see some of the examples that we found in the literature. They were in different sources, and those that you can see are the ones that Rob already talked about, as the Enterobacterales resistant to extended spectrum cephalosporins or fluoroquinolones. An important remark was the data gaps that we faced. There is really a huge number of data that we lack, and especially in the plant and aquaculture sectors. And this relates to different aspects that we need to really understand the contribution of the of the environment of food producing, the food production, to really have a complete view about the impact of this sector. And as also Rob already mentioned, there is really a lack of demonstration of introduction into the food products of the antimicrobial resistant bacteria or resistance genes that were reported in sources, in environmental sources in this food production, let's say, compartment. Regarding the risk factors for occurrence and persistency of highest priority bacteria and resistance genes, we know, and was already mentioned, that antimicrobial use is the most important driver of resistance in terms of selection, in terms of emergency, and this was also pointed out by the experts, also inadequation or deficient application of biosecurity measures. And then we have also identified some bacterial traits that can promote the persistency of a resistant bacteria. Let's say the possibility of biofilm formation by certain resistant bacteria. Also the fact already mentioned that some bacteria are also co-resistant to metals that are used for feeding animals. And also we know that replacement of animals in environments with the persistent contamination of resistant bacteria can also lead to a cycle of continuous contamination of with antibiotic-resistant bacteria. And we also know that the environment, the typical bacteria from the environment, they are the source of several resistance genes, so they can also have here all the tools to have the right genes under a selective pressure that will be applied. As mitigation and strategies options, apart from the prudent antimicrobial use, that is one of the key issues for trying to reduce this burden, a correct implementation of effective general measures like good hygiene, practice biosecurity, as a consequence of also of already mentioned, are important for tackling this problem, as well as other measures that can tackle the source that we identify as the most important one. And I'm referring to the fecal contamination. So all the strategies that can lead to wastewater treatment, reducing the amount of antibiotic-resistant bacteria and genes, or reducing raw sewage, that can contribute to mitigate the problem. We also looked for possible new strategies more specific for antibiotic-resistant bacteria and antibiotic resistance genes, like CRISPR-Cas, and also phages, but they are really in the early phase of research and development. And today we also have later on a presentation about CRISPR-Cas that you can have more, that you can also have more insights about the possibility of using in the future this type of mitigation. In terms of research policies for the future and the ones that will be more urgent ones, the experts convened that One Health-based studies and surveillance that tackle and leading to data quantitative data on different types of threats, like means antibiotic-resistant bacteria and antibiotic resistance genes, with prioritization for emerging highest priority bacteria and resistance genes should be one of the research priorities for the European Union, as well as research studies that can validate practical efficacy mitigations methods for reducing the contamination by this threat. Also, studies linked to the assessment of the effect of recent and future policy developments affecting food-producing environments, the antimicrobial use, and climate change impact should also be carried on, as we know that right now there are different policies in this respect, as the European Green Deal, as well as the Veterinary Medicines Products Regulation, the new one. For ending this talk, as a take-home message, I will mention that antibiotic-resistant bacteria and antibiotic resistance genes are really present in different sources and in different sectors. The real dimension of the problem is not possible really now to know it due to the lack of data that I already mentioned, as well as the impact of this contamination in public health. In terms of priority for intervention, biosecurity is for sure a way to go, as well as antimicrobial use reduction in humans and animals, as well as proper use of the antimicrobials. Also, reduction on the fecal contamination of different sources that impact the food products sector should be also pursued, as well as sustainable new production. And finally, in which consider the most important research aspects to suggest the ones that will tackle this One Health perspective and studies of surveillance with the priority for the aspects that recently or in the near future will be affected by the new initiatives at European level. And with this, I would like to thank your attention and also the support of Beatriz Guerra in the preparation of this presentation. Thank you.
Yeah, thank you very much. So now we have the other side of a coin. I picked up a few keywords like reduction of fecal contamination, wastewater treatment, make sure that we have clean irrigation water, also the issue of biofilm. But let's see what we have as questions.
So we have the questions on the screen. So the first one is if EFSA will give a recommendation about microbiological indicators for surveillance in aquaculture, or about an appropriated approach.
Is it working? Yeah. Yeah, it's working? No.
No.
Another one.
Hello?
Yes, this is working. Okay, so EFSA will not establish any set of limits because this is not on remit of EFSA. But I would say that even if EFSA will have this capacity, still, as I mentioned, we lack a lot of data in order to know what will be the impact of the current threats that we can find in the aquaculture sector, and therefore this will not right now the possibility that will be on the near future, as I see the issue. So I think that this will be for a later stage when we'll have more data about really the current risks associated with the aquaculture sector that in the EU we still don't have. We lack really data on this respect.
Okay.
We have time for 1 or 2 questions maximum.
Okay, I would do one to you in relation to Robert, in relation to the presence of antimicrobial resistant genes from poultry in humans. UTI, E. coli is obviously concerned, and we are many strains, those which are commonly associated with UTI infections, as opposed to food animal associated or endemic E. coli. So, do you think that the problem of having poultry associated strains in humans is really a problem? And if we have any epidemic E. coli that are spread in the human population, and if the presence of these genes, resistant genes, has an effect on the public outcome and the clinical outcome?
That was a difficult one. Well, let's try one at a time. So the thing here is that what has been done is a pure genetic study on this one here, where we are identifying poultry markers, bird markers, or avian markers in the core genome of the E. coli. This is an adaptation that happens when E. coli is growing in different organisms. We have seen exactly the same in Staph aureus and the livestock-associated MRSA. Bacteria adapts to the host they are living in, and it is those markers that we then have looked at. So what we have known for a long time is that we have sublineages of, for instance, this is a bit technical, the ST131, which is one of the really big human pathogenic lineages. We have sublineages there that we have been able to see the same sublineages both in human and in animals. But the problem has always been, is there a direct linkage or not? Is these just coincidental sublineages? But what we think there is with these here is that it is now that these bacteria actually recently has been in poultry, because otherwise they are getting rid of these markers here. Regarding the virulence of this, well, this is a bit like the 131. Sometimes you are lucky, or we can say COVID. Sometimes you are unlucky to have a strain which is more virulent. This is not the same that it is more transmissible. So the Omicron is very transmissible, not that virulent, but the Delta was quite virulent. Sometimes you actually hit both virulence and transmission, and that is where we really see the problems.
Okay, thank you very much. Domenico, I don't know from your side.
Well,
if you have
thank you. I think we have a good introduction for the remaining of the discussion. So we will leave the stage for the next presenters. Thank you again.
Okay, for the next session, I call on the stage Lieve Herman, that she is also co-chair of the next session and will sit with me here. And I call online Barbara Freisen and Caroline Wiley. That should appear at a certain moment on the screen.
Right. In theory, you should be able to see us, hear us.
You can see me, we cannot see you? Okay. So, Barbara Freisen from the European Medicine Agencies, and we also have Caroline Wiley from the European Environmental Agency. So thank you very much. And all our speakers for this session are online. I give you the floor to both of you.
Thank you very much, Beatrice. And in the next session, we will look at the influence of climate change and agricultural practices on antimicrobial resistance. Part of the latter is the use of veterinary medicines, including antimicrobials in animals, and that is very dear to my heart. And at this point in the introduction, I would like to point out that is also a field where significant progress has been made in the EU on a voluntary basis that has now been supported by a very strong legislative basis. You will hear more about it during the next presentations, but in the reports on sales of antimicrobials for use in animals published annually by the EMA, we see the progress that has been achieved since 2011. Overall sales fell by 43%, and sales for certain antimicrobials considered critically important for human use, in particular third and fourth generation cephalosporins and polymyxins, including colistin, fluoroquinolones, and other quinolones, fell by 33%, 77%, 13%, and 85% respectively. So we can make progress, but of course more can be done, and you will hear about it in the presentations afterwards. But I would just like to point out that we now, since the 28th of January, have a very strong legal basis to do even more work through responsible use of veterinary medicines, including antimicrobials in animals, based on Regulation 2019-6 that entered into application on the 28th of January. Only on Monday, Commissioner Kyriakides, during a celebration to mark the entry into application of the regulation, called it a cornerstone of the EU's fight against AMR in a One Health approach. And you will also hear in the presentations that the veterinary medicines regulation is supported by other regulations and other information that give farmers and veterinarians alternatives to ensuring they don't even have to use antimicrobials in the animals under your care. So let's hear about where we are today, so that in the future we can hopefully meet again and report on progress. And with that, I would like to hand over to my co-chair, Caroline Wally. Caroline works at the European Environment Agency, mostly on chemicals and water, and focusing particularly on the EU Urban Wastewater Treatments Directive and on chemicals under the Water Framework Directive. She's very interested in the importance, responsibilities and opportunities of treating our sewage to protect human health and the environment. Her interest in AMR came out of research undertaken by the UK as part of his efforts towards meeting water quality standards downstream of urban wastewater treatment plants. Caroline studied environmental science in Plymouth before working at the Water Research Institute. And with that, I give the floor to you, Caroline.
Hello, thanks, Barbara. I'm sorry I can't join you in the room today, but the plane gods decided I wasn't going to come. So today's discussion is really timely from a water perspective. The EU water legislation is going through a refit, and so there are evaluations and revisions of some really quite old directives. For example, we're expecting a revised proposal of the Urban Wastewater Treatment Directive really quite soon, maybe before the summer. And both the bathing water and the sewage sludge directives are under evaluation. So this is giving us an opportunity to reflect concerns about antimicrobial resistance in European legislation that typically hasn't been revised for 30 years. Okay, so it's a great opportunity to hear about how we might hear from research that can inform that policy. We're going to hear some really interesting talks linking some of these key risks facing humanity over the next decades. We've got climate change, we've got AMR, and I'm really quite excited to see what our speakers have to say. I'm just going to remind the speakers we've got quite a tight timetable and we're going to be quite strict, okay? But anyway, moving on. So for our first talk, I'm delighted to introduce Dr. Amy Pruden. Dr. Pruden is a university distinguished professor at Virginia Tech in the USA, and she's working in the Department of Civil and Environmental Engineering. Her research focuses on advancing the means of monitoring and mitigating the spread of pathogens and antimicrobial resistance in the environment, including in water, wastewater, and agricultural systems. Dr. Pruden, please take the floor.
Well, thank you so much for the introduction, and it's truly my honor and pleasure to join you all in this really important conversation about the silent pandemic of antimicrobial resistance. And so what I'd like to do is for our next 10 minutes together is to contemplate some of the intersections between another existential threat facing humanity, and that is climate change. So both climate change and AMR have a dire trajectory and dire consequences of inaction. So we know with climate change, we have sea level rise, heat waves, droughts, floods, wildfires, water scarcity, and overall unpredictable weather hurting agricultural production and food security, and many other consequences, such as increased displacement of human populations and loss of habitat and shifting habitats for wildlife. In the case of antimicrobial resistance, we have antibiotics losing efficacy for treating dangerous bacterial infections. And we see that routine surgeries can become much more dangerous. There are vulnerable populations to AMR as well, especially neonates and immunocompromised people. And it's not just antibiotics, but other antimicrobials are losing their efficacy, such as fungicides. And we're looking at a post-antibiotic era if we don't do anything about this. As an environmental engineer, I tend to see the problem of AMR from an environmental lens. And this was illustrated very nicely in this UN Environment Frontiers report that came out in 2017 and highlights water as an interconnecting thread that receives multiple sources of antibiotics, ARBs, and ARGs. Of course, we've talked about livestock use, and that includes aquaculture, but also emissions from manufacturing and from wastewater treatment plants. And water is really critical. Water is life. We need it for drinking, cooking. It's also used for recreation. And so there's multiple exposure routes that we're concerned about here. This also illustrates the complexity of the problem. You might have seen this recent USAID report came out that specifically highlights linkages between climate change and the expectations there, such as rising temperature, more extreme weather, rising sea levels, and antimicrobial resistance. So what are some of the specific concerns? Well, obviously, temperature is fundamental to microbial growth. So pathogens and microbes in general will have higher metabolic rates and higher growth rates. We're also going to see a shift in the ecology of both pathogens and their vectors for spreading, an opportunity for emerging disease. We're also seeing the increased storm events, and this is increased opportunity to disperse antimicrobial resistance through the environment, including the water environment, but also we're seeing studies of it spreading through the atmosphere. Human populations are more vulnerable after a natural disaster and more likely to acquire infections. And we see the coastal, peri-urban, and well water communities are likely to be most affected. And finally, another big one we'll hear about is water scarcity. That means we need water reuse. That means we need to think about water reuse technologies because they're not intentionally designed to remove AMR. And since sewage is the water source, we need to intentionally address the removal and attenuation of AMR. I wanted to share this example of a study that we did in Puerto Rico. You might remember a few years back that a Category 5 hurricane devastated this island in 2015. So for over 6 months, people lived without power and electricity. That meant that wastewater treatment plants and drinking water treatment plants were not operable, and there was not access to safe water. Now, this study highlighted the importance of surveillance. We did not know the storm was coming, and there was not a baseline before the storm. But what was very apparent is that the signatures of ARBs and ARGs in the wastewater treatment plants were very apparent in the watershed where they were impacted by wastewater treatment plants. So you can imagine storms will spread that and disseminate AMR throughout the watershed. Another example you may not be familiar with is Naegleria fowleri. This is a parasitic pathogen, also known as the brain-eating amoeba. Now, this organism loves hot water. And we see that although infections are rare, they are most common in the warm southern regions of the US, like Texas and Florida. But we see the most recent infections are actually northward and more recently in Minnesota. And if you've been there, that's quite a chilly climate. So this is a surprise and a concern. And I point this out, why? Because bacteria also grow faster at higher temperatures, and the escape pathogens in particular that we know are a major concern for antimicrobial resistance very much prefer these warmer temperatures. So we're talking about tackling a grand challenge, and much can be learned from efforts to address climate change. We're talking about complex, multifaceted problems. We have to communicate effectively to the public. We also have to make sure that we get the science right and that we're giving good advice. And we have to understand and address barriers to action. So what are the perceived and real trade-offs? What are stakeholder perspectives? What is the political will? And the reality is that often most immediate problems tend to get attention, but what we really need is a holistic approach from the beginning. We need systems thinking to avoid unintended consequences. And one key way to do this is to identify synergistic ways that we can act that have multiple benefits. Now, with climate change, some of the actions have, of course, been the Paris Agreement and efforts to reduce carbon dioxide emissions and efforts to mitigate greenhouse gases. We have analogies with antimicrobial resistance. We have the WHO Global Action Plan and efforts of the quadripartite and being translated into national action plans. And a big part of that, obviously, is reducing antimicrobial use, but also we're seeing talk about reducing emissions of the ARB and ARGs. In terms of mitigation, there are many opportunities and fronts on which we can move. I mentioned wastewater treatment as one specific example from an environmental perspective. There's technology and innovation. Again, numerous opportunities. Vaccines and diagnostics are two that can help to reduce and optimize use. And important to think about, antibiotics do serve a critical role in human health, and so we need them when we need them, right? And so improving access for vulnerable populations, but making sure that use is appropriate. So what is an example of a synergistic solution? So you could say locally relevant cultivation practices that reduce greenhouse gas emissions, reduce nitrogen and phosphorus emissions, and also attenuate antimicrobial resistance.
You have 1 minute left. Okay, thank you.
So in closing, I hope you're all aware of this UNEP report that came out specifically for policymakers, and it highlights the triple planetary crisis of climate change, biodiversity loss, and pollution and waste, and all of which are a result of unsustainable consumption. I'm sorry, my slides went away. 1 minute, I lost my, there we go, okay. And Finally, the G7 health ministers communication identified 3 main fronts: the pandemic, obviously, the antimicrobial resistance silent pandemic, and climate change. And just in closing from that report, we need cross-sectoral surveillance capabilities that aim to cover all countries, multiple pathogens, antimicrobial resistance, human, animal, environmental, and climate-related inputs as part of a One Health approach. So thank you for your attention, and I look forward to the discussion.
Okay, thank you very much for that really interesting talk from an area that I have to learn a lot about. I would like to introduce the next speaker. It's Dr. Junxia Song from the Food and Agriculture Organization of the United Nations. Dr. Song has extensive experience in preventing and controlling zoonotic diseases, transboundary animal diseases, and antimicrobial resistance. As I mentioned, she works at the FAO, but at the joint FAO-WHO Center on Zoonotic Disease and AMR. She's the FAO AMR contact focal point and unit head and leads development and implementation of the FAO Action Plan on AMR, and significantly contributing to the AMR quadripartite activities. Dr. Song has a degree, a PhD in veterinary medicine from the China Agricultural University. Dr. Song, the floor is yours.
Thank you for the introduction. First, can you see my slides?
No.
I already shared.
No.
No? Just a moment. This is something, sometimes I have this problem.
Now.
Is there?
Yes.
No?
Yes. Yes, now we can see them.
You can see now?
Yes,
okay. you can continue.
But I don't know if
Okay, good.
Yes.
Good. Thank you. I'm really, really glad to be here to join this very interesting and important topic. EMR is not just a health issue. EMR is strengthening development, compromising the achievement of SDGs. So in this slide, we detailed some mentioned the impact of EMR in the global development by looking at the SDGs affected. As per the report published by World Bank in 2019, we can see how EMR as a whole impacts several SDGs. In the second group, we can also see the SDGs that are directly affected by the impact of EMR in agri-food sectors, and such as zero hunger, SDG good health and well-being, clean water and sanitation, and SDG 14 and 15 is life below water and life on land. So as mentioned, it's not just an issue of health, it's a development issue. Let's look at a bit more detailed linkage between AMR and the agri-food sector, in particular in relation to the food producing environment and system. Agri-food systems are facing all-time challenges as the global food demand is rapidly rising. As a consequence of this increase in food demand, current agri-food production systems need to transfer themselves if they are to provide the required food security in the future. However, food security can only be achieved if the result of the transformation are sustainable production systems. And to ensure sustainable, the transformation must be taking into account the issue not directly related with the production, but yes, this is some of the most pressing problems need to be considered in the transformation, and we listed here, for example, the production and preservation of natural and agri-food environment contributed to reduce climate change. It was elaborated very well by our the previous presenter, and contribute to reduce AMR. Looking at the transformation of agri-food systems, we found that I hear some echoes. Can you hear me?
Yes. Can you hear me?
Okay.
Yes.
So
please go ahead.
looking at the transformation of agri-food system, we find that actually it's already starting to happen. But it is not surprising if the world is expected to produce in the next 30 years the same amount of the food that has produced in the last 10,000 years combined. Well, this represents a major contribution to achieve SDGs. It also comes with some associated risk. Intensification farms as well understand it is associated with the use of antimicrobials. FAO path towards this agri-food system transformation is outlined in 4 pillars. Scale up of emergency agriculture assistance, invest in agri-food systems, and science and innovation, and food loss and waste. So let's take a future change in livestock sector as an example. So this is another angle to looking at climate change and livestock sector. Climate change has intensified the spread of transboundary animal and plant disease, animal disease and plant pests. And among 58% of the animal diseases identified as most important to poor livestock keepers are sensitive to climate change. And the increased prevalence of animal disease can drive EMU and burden the risks associated with AMR. Therefore, transformation of agri-food systems that consider 2 different issues like climate change and AMR, this is exactly an example how 2 different problems link and synergies in a solution to apply. This could be applied in other sectors. For example, aquaculture, beekeeping. So those are all widely AMR and antimicrobials are being widely used in those sectors. So I'm really glad to say many of our speakers already mentioned One Health. We often say that global changes require global solutions. One Health was pioneer in that respect by breaking silos towards a common health goal. Today, learn from the success of One Health experiences, we may need to upscale the idea behind it and apply it to the main global challenges as we are facing today. For example, climate change, we mentioned, biodiversity, food security, protection of environment, and of course, combat AMR. So actually, antimicrobials as a precious discovery, its use has allowed to save millions of lives. It contributes a lot to food systems, to human health, to animal health, to provide food at levels that was impossible before. However, we have reached a point where its use in our current agri-food production system is not just to provide positive outcomes, it also compromising that use. For example, it has been estimated, I think this is Dr. Robert also mentioned this, more than 70% is 73%, that's estimated number, all antimicrobials sold globally are used in animals raised for food. And besides that, antimicrobials are also used in crops to treat bacteria and fungal diseases. And a considerable amount of antimicrobials are used in aquaculture production in LMIC countries. And as we mentioned, it's also used like in beekeeping sector. So currently, it's obviously reducing the need of antimicrobials in agri-food system as being impressive, and it's clearer than ever. So here I highlight as I reduce the need And the point is, we are thinking because the farmers, if they really need, they should use. But we need to look at the needs. We try to highlight and reduce the need. If we talk to the farmers, say, okay, you stop to use antimicrobials. So what are other solutions? So reducing the need in agri-food system, we can see have really a positive knockdown effective in many aspects. If we reduce the need in production, we will reduce the residues in products, milk, eggs, meat. It can reduce the AMR discharge to soil, to water. So now the priority of reducing the need should be given to the actions at production level, at farm level. But of course, we cannot ignore the rest of the food chain up to consumer from farm to fork. FAO has developed an action plan on antimicrobial resistance, including 5 objectives, such as increasing stakeholder awareness and engagement, strengthening surveillance and research, enabling good practices, promoting responsible use of antimicrobials, and strengthening governance and allocating resources sustainably. And to adapt to future changes, need to emphasize an evidence-based policy and intervention. So it's about data sharing and data generation. So the tripartite organization WHO or UA is already now changed to UA, and at FAO we made joint efforts to establish the integrated surveillance system to support data management and sharing. From FAO side, FAO International Antimicrobial Resistance Monitoring System, in the short term is INFAM, is a part of this joint effort. So we are aiming to collect data on AMR in animals and food commodities, and also collect EMU data in crops. So now INFAM is being established and it was pilot. Now we are in a pilot phase, and so it will support the countries in collecting, analyzing, and using AMR data for animals and food for their national implementation, their national action plan.
1 minute.
Okay, the 2 words for take-home message. Number 1, reduce the need. Reduce the need for antimicrobials in agri-food systems to combat AMR. The second one, I think, is repeated many times. That's One Health approach. Keep refining the One Health approach to better link development and AMR. Thank you for your attention.
Thank you very much, Dr. Song, and I'm sorry for interrupting you during that. In that talk, you highlighted the challenge of meeting Sustainable Development Goals while also combating AMR through reducing the need for antimicrobials and agri-food systems. I think this is really demonstrating the need, the very complex interactions when we're thinking about in the environmental world, how we're going to do these things and achieve multiple goals all at the same time. Now we're going to move on, and I'm very pleased to introduce Dr. Despo Fatta-Kassinos. She's a professor at the University of Cyprus, working in the Department of Civil and Environmental Engineering. She's got really wide research expertise, including in water and wastewater treatment and reuse, contaminants of emerging concern, advanced biological treatment, antibiotic resistance in the aquatic environment, and the uptake of micronutrients by crops during wastewater reuse. Dr. Despo Fatta-Kassinos, please take the floor. Thank you. You're muted. Yeah. Sorry, you're muted, please.
Apologies for this.
Yes, now.
Okay, now.
So everything okay now?
Yes, here in the room, yes.
Okay, thank you very much. Good afternoon, everyone. So today I'm going to talk about the current challenges regarding the ongoing developments concerning the need for reclaimed water reuse for irrigation purposes. So water scarcity already affects every continent, including Europe. Water use has been growing globally at more than twice the rate of population increase, and agriculture was and still is the major water consumer. When a territory withdraws more than 25% of its renewable freshwater resources, it is called as a water-stressed region, and already 2.3 billion people live in such areas, while 3.2 billion people live in agricultural areas with high to very high water shortages, while 1.2 billion people, which roughly corresponds to 1/6 of the world's population, live in severely water-constrained agricultural areas. And this is where water reuse practice come in as a solution to alleviate the problem of water scarcity. Water reuse practice comes along with various benefits. It preserves water resources by extending the water life cycle. And of course, it's in a full compliance with the strategy of circular economy. The water reuse sector is a strongly growing one. The global market for wastewater recycling and reuse technologies is estimated to grow from $21 billion in 2021 to reach 40 billion by 2026. And we see that the global market for reuse expressed in cubic meters per day was less than 1 million in the 90s, while currently it is foreseen to even surpass 10 million cubic meters per day in 2025. On this slide, you can see the location of the various wastewater treatment and reuse facilities in Europe. We have 250 located in Northern Europe, while 537 are located in the southern part of Europe. In these numbers, we include both non-potable and direct potable uses, spanning from agricultural to landscape irrigation, and from industrial uses to the augmentation of water supply resources. Agricultural reuse is the most common water reuse application in Europe. So as we all know, the conventional activated sludge is on a worldwide level, the state of the art. So this process was developed in order to reduce the organic load and the nutrients from the urban wastewater. But when this process is operating very well, it may reduce the microbial load up to 2 to 3 log units. Even in that case, though, the secondary effluent is able to supply into the environment up to 10 to 12 antibiotic-resistant bacteria per day, or 10 to the 18th antibiotic-resistant genes per day, for example, encoding for beta-lactam resistance. And even though we have this microbial reduction, what we have seen through the various studies during the last decade is that the cultural antibiotic-resistant bacteria and genes prevalent in the total effluent bacterial or genetic component concentration in the effluent is increasing, and that the intra and extracellular DNA content undergoes very limited reduction. And this is why we test membranes to combine them with a conventional activated sludge and increase the efficiency. And what we see is that the free DNA, or at least part of it, is able to escape membranes. Also, we test a number of technologies that are able to disinfect wastewater. And what we see is that these disinfection technologies, at least some of them and at some degree, they create some very harsh conditions that may act as selective pressures. And what we see is that we may have a selection of resistance, again, in the prevalence in the end of the treated wastewater. And something that is very also relevant to the reuse practice is that when these harsh conditions go away and more favorable conditions prevail for the microorganisms, these are able to repair their damage and regrow. And if we consider that during the wastewater reuse practice, we do have to store and transfer wastewater, the regrowth potential is very relevant. So we have some important questions here that we really need to address. At the moment, we don't have a very deep understanding about the presence of antibiotic-resistant bacteria and genes and other mobile genetic elements in the treated flows. We do know some more about the antimicrobial compounds presence in the treated wastewater, but what we don't know is about the They are metabolites or they are transformation products that are generated through the various treatment processes at the treatment plant. And what is important to note here is that some of these metabolites and transformation products may continue to have in their molecular structure the bioactivity. So they are bioactive compounds as well. And of course, the co-occurrence of all these with other chemical stressors is not exactly understood very well currently. And all these questions are very relevant both for the direct reuse and also about the indirect reuse. And this discussion leads to the most important question: what is the actual impact of the wastewater discharge and reuse into the environment, on the terrestrial environment, including the soil, the microorganisms, other organisms, on the air and aquatic compartments, and on the crops, and consequently on the human gut and human health. And this question concerns not only the presence of bacteria and genes, but also the co-occurrence of them with antibiotics, other antimicrobial compounds, and transformation products. There have been numerous projects on a European and international level addressing these questions. And here I present to you the concept of the Answer Marie Curie ITN project that I had the pleasure to coordinate. In this project, we have looked into various treatment technologies, the fate of AMR on soil, the aquatic environment, the potential for crop uptake, and we have used advanced effect screening, advanced chemical analysis tools, and biodetection systems in order to be able to provide some input to contribute to a scientific base for risk assessment. So during the last years, we have seen several studies coming up in relation to the accumulation, the potential accumulation of resistant genes on soils irrigated with wastewater. And even though the various studies are very different in their design, what we see is that we are getting contradictory findings. For example, the first example concerns a study that was performed in Israel. And there, the researchers found that the ARCS levels in wastewater irrigated soil were on the whole identical to those in freshwater irrigated soil. While in the second example, we see that the relative abundance of selected genes was significantly higher in wastewater irrigated soils. And here, another example where the researchers found that over 100 genes were significantly enriched in the irrigated soils. However, we are not at the current time able to talk about the uptake of genes by crops. We don't have systematic studies with concrete results, but we do know more about the potential uptake of chemical compounds by crops. We have seen various studies coming up. Each of these studies, however, is focusing on different compounds, is using different crops, and for sure the human exposure through dietary intake is until now much less studied. So we do know that the uptake of pharmaceuticals, including antimicrobials by crops, may be influenced by a variety of factors, be it biotic or abiotic, like the plant characteristics and physiology, the environmental characteristics and growth conditions like the soil and the irrigation techniques, and also the physicochemical properties of the organic compounds. We know that non-ionic compounds tend to be transported predominantly in the direction of the transpiration stream, and therefore they tend to accumulate in the leaves, while ionic compounds like trithometoxazole is trapped in the phlegm and is potentially present in higher accumulation in the fruits. So the better the fruit's ability to transpire water, the higher the risk of pharmaceuticals accumulation within the fruit. Another important characteristic of the crops is that they are able to metabolize some of these antibiotics, and the metabolites that they are present in the crops continue to be also themselves bioactive. So, in general, it is difficult to draw concrete conclusions because the data in the literature are available for different plant growth methods, different plants and compounds in each study, and they apply different experimental conditions. So my key message today is that we really need more field studies to shed light on the uptake of antibiotics and antimicrobials by crops under actual and realistic agricultural conditions. We need to consider for our risk assessment methodologies not only mixture of parent compounds, but also the transformation products that continue to be bioactive. And we really need studies not only to qualitatively understand the problem, but studies through which we will be able to quantify the problem. And my message is that in this story of wastewater reuse or reclaimed water reuse, is that in this case, low abundance does not mean necessarily low risk. Thank you very much.
Right. I hope everybody in the room is clapping. For some reason, I can't hear the room, but it was definitely an inspiring talk, and particularly highlighting a number of research gaps in your area of expertise. And so I hope there are people in the audience who will take it up and further both the research, but also the development of appropriate policies. Our next speaker goes back to an area which I understand a bit better. And it is my pleasure to introduce Dr. Christina Greko from the Swedish Veterinary Institute. Dr. Greko is not only a veterinarian, but she also has a PhD in veterinary microbiology. And these experts are few and far between. So not only at the European Medicines Agency, we rely on her expert input, but also ECDC relies on her. And Dr. Greko was the chair of the expert group, which developed the most recent JIACRA report, and that will actually be the topic of her talk. So, Christina, the floor is yours.
Thank you so very much, Barbara. Yes, we can go directly to the next slide, or rather I can take control. Yeah, all these techniques, after 2 years, we have still not managed. It's absolutely fantastic.
We have lost you. I hope the technicians above can take care.
Have you lost me completely?
No, from the screen we cannot see you or the slides, so I hope in 1 minute it will be solved. I'll let you know.
Okay, thanks. I'll stop the clock for a while.
Yes.
Can you hear me?
Yes, perfectly.
All right, I'll try to economize on time. What I'm going to present and talk about, is it all right now?
Not yet.
Not yet, okay. You just shout when it is. There, I can see that you can see me. Wonderful.
No, only the online ones. We cannot see you here. I think they are working on it. But we are happy to hear you, Christina. You can talk in the meanwhile. Should
I instead share my presentation from my computer?
The problem is we see a slide with the logo of the conference. We cannot see anything else. But just a minute. Now we see you.
Fine. Then I just have to switch slides to get that to work. I need to take control again because they unselected me. Now, somehow, I'm going to talk about the, it doesn't work, the control of switching slides, but maybe it works. Lots of technical problems and we are running towards the end. I'll do it that way. I'm going to talk about analysis of consumption and resistance on both sides, in the human sector and in the animal sector. The JIACRA report mentioned is a report where we use existing systems, existing monitoring systems, and reuse that data. We pool them and we analyze what possible connections there are between consumption and consumption, between consumption and resistance in animals. You can see the square angles in the slide. So these are the potential links that we investigate in these reports. A little bit of the results, but just a flash of some of them. Good news, Barbara already mentioned that, is that in the earlier JIACRA report, consumption for animals was higher than for people, but now it is going in the right direction, and it's absolutely where it should go. So it is lower. It varies between countries, though, so it's not the same in all member states, or reporting countries, rather. What happened with the animal consumption? Well, Barbara already touched on that as well. There have been huge efforts in quite a few member states to reduce the need for antibiotics, some voluntary and some push and pull mechanisms. The method varies as everything in the European Union. And it's also encouraging that some of the more critical antibiotics are decreasing. Those are the ones with the bars towards the end, where Barbara highlighted colistin, that after scientific findings of a transferable resistance type, EMA produced an assessment and said that it needs to be reduced to under 5, but preferably under 1. This report contains many analyses, and I recommend, if you're after something in particular, to look at least at the summary, which is a little bit more accessible. Apart from that, it goes quite heavily into science, so to speak. But if I want this, on the left side, you see the antibiotics that we have selected for analysis. And on the top row of this graphic, you see the bacteria where we have a match, and where there is nothing, there is not a match. We don't have enough information in both sectors, so to speak. What we find is that there is often associations between consumption and resistance within sector. And there is quite often associations between resistance in bacteria from animals. Oh, it should say from humans there, of course. Resistance in bacteria from animals and resistance in bacteria from animals. One analysis that I'm personally particularly fond of is confined to the animal sector, and that is an analysis of the total use of antibiotics on the x-axis. You can see how it varies between countries. And the proportion of bacteria in the monitoring program of EFSA that are susceptible to all tested antibiotics. Everyone does the same. It's fully harmonized and guided by implementing decisions and so on and so forth. So we can really compare. And what you see in these slides is that the more you use, the less susceptible bacteria you have. And this has been consistent from JIACRA 1 until JIACRA 3, and it will stay consistent, I guess, in JIACRA 4 that is currently ongoing. However, what happens over time, of course, is that not only does use decrease, or sales, because that is what we monitor currently, not only does sales decrease, but actually the EFSA monitoring reports show that also resistance is starting to respond. So the situation is clearly improving. In the report, there are limitations, and we can go on for ever about the limitations, but I picked out 2 that I think are important from everyone to understand, and that is what we use is data from systems that are built for other primary purposes. The systems for human medicine are primarily built to look for resistance that, I mean, is it that is of importance for public health, but in the hospitals, is the situation really horrible or not? Is it improving? And Robert showed some pictures of that. It can improve, but it mostly does not. And these are ecological analyses. They have an extremely low granularity without connection in time or space. And this type of analysis is mainly hypothesis generating. In the conclusions, though, supported by other science, we conclude that further interventions to reduce antimicrobial consumption will have a beneficial impact on the occurrence of antimicrobial resistance. And it underlines the need to promote prudent use and infection control and prevention in both humans and food-producing animals. I would like to highlight an earlier report, joint report by EMA and EFSA, and that is what is called the RONAFA report, Reducing the Need of Antibiotics for Farm Animals, from 2017. I so much love this infographic because it gets it all in one picture. What you need to do is to reduce the use by removing unnecessary use and then working for healthy animals. We can also try to replace antibiotics with other alternative treatments, but it's a little bit more shaky there what the alternatives are worth, except for effective vaccines, of course, that can do a lot of things. But we also ultimately need to rethink some production systems that cater for high infection rates. If you ship around animals and mix them together, they will be more likely, it's like the daycare centers, you know, they will be more likely to get a baby infection because they are usually young when they are shipped. We have some tools that I think are important, and Barbara mentioned at least one of them, and that is the regulation of veterinary medicinal products, where I think there are a number of tools in this regulation, and I've highlighted only one here, Article 107.1, that I think is maybe more like a vision than an article in a regulation. But if we all do our best to live up to this regulation, to this article, we will ultimately, in time, be fine. You should not use products, antibiotics routinely to compensate for factors that you can correct by other means. Reducing the need. Reducing the need is also very much supported by the animal health law, where, for example, on transmissible animal diseases, where, for instance, the responsibilities are clarified of farmers, vets, and others are very clarified. And clearly farmers are responsible to have good biosecurity on their farm, which will also support. So these are some push mechanisms. And maybe around the corner is a pull mechanism. I am certainly not an expert on the common agricultural policy and how that works, and I cannot project at all whether the ambition to merge the farm-to-fork strategy with the common agricultural policy will have the desired effect. But the Commission writes in recommendations to member states that a concerted effort is needed to further reduce the use of antibiotics. Instruments that promote best practices and reduced and prudent use of antibiotics and so on. So there could be a pull mechanism here, and generally both push and pull are needed. So thank you for your attention.
Okay, thank you very much for this session. The time is passing, but I think
Yes.
we have some questions and we will try to reduce them. So a first question to you, as last speaker, please, can you answer, should antimicrobial resistant genes, AMRAs, be included in future JACRA surveillance?
I think we must head there. However, just taking what you have, I think we should think about how develop a model for a better integrated genetic analysis. I mean, we must think very carefully, because remember I said we take this from existing systems, and sometimes the analyses are made for a particular purpose, and then the material, maybe the samples you have or whatever it is, maybe does not fit really for this type of analysis. But yes, we must go there, and in particular once we go One Health surveillance, that is including the environment, I really think we must go there. So yes, definitely. Then we get a whole different level of refinement compared to these very much helicopter, and you can't really, for instance, we compare resistance to third generation cephalosporins, but that is 200 things or 600 things, because there are so many genes that potentially is causing this. We know we need to trace one particular gene.
Okay,
Thanks.
that's a clear answer. I continue to the other speaker, Fatta-Kassinos. You have shown that there are many possible routes for antimicrobial resistance transmission in the environment. Can you identify practical steps, such as what should be routinely monitored in wastewater discharges and bathing waters, and the thresholds that should apply? If not, what information do we lack?
Okay, thank you for the complex and interesting question. So first of all, I think the first step is to really, go deeply into this story of wastewater reuse and understand a little bit better the impact of both the discharge and the reuse practices. I also believe that we need a multi-barrier approach for the reduction of antimicrobial related contaminants. I don't think that we have one technology that can solve all the problems. So we need various processes in combination that will apply absorption, oxidation, filtration. This is what I mean with the combination of processes. And also we may have a barrier during the application of wastewater by applying, for example, absorption materials like those that are tested at the moment, including biochar and so on. And then for the second part of the question, for the parameters, I think that we need to identify indicators for all these both chemical and microbiological compounds. And for those bacteria that we really understand some more things, we may look into the resistant part of them and put some percentages to achieve during treatment. Thank you.
Thank you very much. I think this is a very clear answer, and I think the water business is used to handle indicators, so probably this will be successful with this EMR indicators as well. So then we have a question for Junxia Song, and that's about the global issue of antimicrobial resistance. You very well explained that it's over all the global world and that we need to tackle it globally. But what to do with regulations, and how can we enforce them also in states where we have not that power maybe to enforce some regulations and that they are really followed?
Thank you. This is really a very good question. And if we want to keep it sustainable at a country level, so regulations is play a very important role. Actually, at globally, and FAO, we are working with WHO and UA and UNEP. And as a quadripartite, we are working on, at a global level, we are working on regulatory work. We identify this as a priority for the all quadripartite work plan. And this year, we will have a global summit on regulatory. And at the moment, the working group was established among the 4 organizations. We try to looking at the gaps at the country level, at gaps at the regional level, and then we will bring all the expertise from the One Health perspective, covering animal health, human health, plant health, and the environment. So definitely, there will be a lot of work in this area, and try to ensure the sustainability AMR work at a country level, and also regional and global level. Thank you.
Thank you very much. And then a last question before our coffee break. That's for the first speaker, Pruden. And that's about this climate change. It's quite an exciting topic that you bring in this discussion of AMR. And you mentioned also the metabolic activity of these microorganisms, and that when you have higher temperature, that maybe these microorganisms will be more metabolically active, and that would increase their growth and their transmission, as I suppose so. But the question is if that is equally effective for all bacterial taxa, because we have also organisms which like to have it a bit colder. So can you reflect on that?
Yes, absolutely. That is an excellent question. And I think it really speaks to the complexity both of climate change and the science of AMR. And so I think from a scientific perspective, we have to zoom in on these kinds of details, and it will be very situation specific. And so I think what I proposed is a hypothesis. We know that many human pathogens prefer warmer temperatures because the human body, in fact, is a warm ecosystem. And so I think it's a hypothesis that deserves to be examined more closely. But for sure, this won't apply to all pathogens. One study that I saw that came out recently did show that the cost of resistance, so we know when a bacterium carries an ARG that there's an ecological cost, and in some situations, in a good way, a disincentive for them to carry that ARG. But that study showed that when they're at their optimal temperature, they have more of a tendency to maintain the ARG. So I think this speaks to some important scientific work to be done to untangle this complexity. And absolutely, it will be important to do those studies so that we have very targeted mitigation strategies.
Thank you very much. And with this, I want to close this second session. I want to thank all the speakers, the chairs, and also the technicians to lead us quite fluidly through this session. And I think it's time for everybody to have some coffee. And we expect you back at 4:10. Okay, good afternoon. We can start the last session of this afternoon. This is a session dealing with preparedness for our EMR. And in this session, we will look to some new developments related to regulation, to monitoring and surveillance, and also to some new biotechnological tools to decrease EMR. So this session is chaired by Beatrice and myself. So Beatrice is belonging to the EFSA staff. She is a EFSA lead expert on molecular epidemiology and a senior scientific officer at the new EFSA unit, BioHow.
And I have the pleasure to co-share with the person that you have seen close to me in almost all the session, and it's Lieve Herman. She is the head of the Unit of Technology and Food Science at Flanders Research Institute for Agriculture, Fisheries and Food, the ILVO. She is a biologist, and she has a PhD in molecular plant genetics. And she is member of the biohazard panel, and she is member of several working groups dealing with risk, microbial risk assessment. And she is the president of the scientific committee of the Belgian Food Safety Agency. So it's a pleasure to be with you. And with this, we open the session. I have here close to me the two on-site speakers, but we will begin with the online speaker, Rene Hendriksen. Rene, can you hear me?
Yes,
Okay.
I can.
So, Rene is a professor at the Technical University of Denmark at the National Food Institute and leads the research group of global capacity building. He acts as director and co-director of the reference centers for the WHO Collaborating Center, Food and Agriculture Organization Reference Center, and the European Union Reference Laboratory for Antimicrobial Resistance and Genomics. And I have the pleasure to have worked with him and very close during several years. So, Rene, the floor is yours.
Thank you, Bea, and thank you for inviting me. And I apologize if I cough a bit. I'm homesick with COVID. But anyway, let's just jump into it right away. So my presentation is more a holistic view on how prepared we are for surveillance of AMR in food production environments, and basically just to. Does my slide move?
The technicians will move it.
I'm sharing the slides.
Okay.
But they're not moving. Let me see.
Rene, if it's okay for you, the technicians can share it because this caused some problems with our other speakers. Is okay for you?
Yeah, that's fine.
Okay.
But as I said, let's wait a bit. Thank you. So next slide, please. Thank you. So as indicated, I'll jump directly to the subject. So we have already heard from Ruppitsch about the emergence of AMR worldwide and that we are in the midst of a silent pandemic. So basically, maybe a bit provoking title here that no lack of evidence, lack of action. So basically, I think we have enough evidence. What we need is to strengthen our surveillance and take action. And this is by building global capacity building for disease surveillance. So basically what we really need is more surveillance, more data sharing in real time, but also the comparison of data from multiple sources. And this refers, of course, to One Health. And also using multiple methodologies. So this could be phenotypic methods, it could be more molecular techniques, could be whole genome sequencing, even metagenomics. So basically, our current surveillance and outbreak detection are really not adequate. It's too late and too fragmented to take proper action to respond to public health crisis. So we need definitely to improve the detection and by that also sharing the data. Next, please, slide. Thank you. So basically, the current state of play is that WHO, FAO, UNEP, OAE, EFSA, EC, and many others have already emphasized the importance of focusing on the risk of AMR transmission in a One Health context, including also the environment, and integrate this for the future monitoring programs. And there's already a number of guidelines, protocols available that have been published online. So I just included a few screen dubs of some of those. Many of them have already been mentioned by other speakers, but maybe just to touch upon one, which is, of course, the latest one from UNEP, the environmental dimension of antibiotic resistance. So all of these address the risk of AMR transmission in the environment, and also touch upon how this can be investigated further in a surveillance context. Next, please. So basically, there's plenty of data, but we need to also take action. So I think it was Caroline that also mentioned a few regulations. So we have the regulation for water quality, but also the one for minimum requirements for water use. And as Caroline mentioned, these just briefly touch upon AMR, but as Caroline also said, these are being evaluated and updated, which is of course very timely. A few years ago, there was also an EFSA technical specification being issued on the harmonized monitoring of AMR in zoonotic and indicator bacteria from food-producing animals. And here there was actually also a proposal to carry out a baseline of AMR from domestic produced shellfish. So this was indicated as a matrix that potentially could be used in a future surveillance. I had in the past also a discussion with Domenico from ECDC about this, that there's also evidence how this can be used simply to collect shellfish from domestic farms, from rivers or deltas, because there have already been several papers indicating how these can uptake antibiotic resistance pathogens that would represent what is also coming from the food producing environment. Next, please. So currently we have just started the latest 6 or 7 years term of the EU monitoring for food and the veterinary sector with the Commission. And this is just to indicate the current play. And basically, the focus is still on Salmonella, Campylobacter, indicator E. coli, and then a specific monitoring of ESB, LAMC, and Campylobacter producing E. coli. The concept is a rotation. So every second year, it's a poultry year. The opposite year is a cattle and a pig year. And basically, the concept is that everything is harmonized. It's based on dilution methods, and the interpretation criteria is according to ECOFS, and everything is very comprehensive and detailed in terms of the sampling design as well. The UL facilitate training, proficiency testing, and confirmatory testing. So by that, this is just to indicate that there's already a system in place, especially in the food and the veterinary sector in EU, where we have already established a harmonized and standardized monitoring. So basically, according to the previous slide with the technical specification and the idea proposal of setting up a baseline, this can easily be implemented in such a framework as we already have established, as indicated in this slide. Next, please. So, as already mentioned also by Luisa, that EFSA have just issued a scientific opinion about the environment and the emergent spread of antibiotic resistance through the food chain. So Luisa already touched upon a few of the recommendations, but I have just indicated here also parts of the conclusion. So basically, there's a need for One Health-based integrated studies, which is of course harmonized and with also concrete strategies for how to set up the monitoring and the surveillance. And here, of course, the priority is to focus on sensitive and standardized methodologies, equivalent to what I have just explained about the EU surveillance for food and the agriculture. So this can, of course, focus on the important antibiotic-resistant bacteria and genes. And what is also important is to ensure that it defines the sampling strategy, because this is really vital if we want to have a strategized and standardized approach for the future. On top of that, we also need long-term longitudinal cohort studies. And this is to use quantitative methodologies, potentially also a metagenomic approach, focusing on the highest priority antibiotic-resistant bacteria. Next slide, please. So in terms of improving the preparedness for AMR, it's important to ask the question, what, where, and how. So Robert also mentioned the grant paper that was just issued and published in Lancet. So here it's just another figure from the same paper indicating a number of pathogens that would be of high priority. But there's also other papers that show more or less the same. So basically, we need to decide, so what are the risks for public health? So there's plenty of domains, and these domains have already been mentioned in many of the guidelines or protocols that I mentioned earlier on. But it's important to identify, so what are the risks and where do we want to collect the samples from? That's the next question. Because again, it's important to know the domains we want to target. And then, as I said, what is it we focus on? What pathogens and what samples? Should it be, as Robert indicated, pathogens, or should we actually go for a more metagenomic approach? Next slide. So despite all our good intentions, I think that personally, the only program that have really started to look into One Health surveillance or study, including the true One Health concept, including also the environment, are probably the Tricycle project initiated by the Tripart and now the Quad part, since the UNEP have now joined the consortium. So basically, this built on a concept focusing on ESBL, AMC, and carbamazepine producing E. coli collected from food environment, from the environment, and from humans, and being, in my opinion, a truly One Health program. Next slide, please. So this is, of course, one approach. As I mentioned, there's also another approach, and again, sewage water, wastewater have been mentioned in many of the reports as well as a matrix to use. Could also be animal feces. So basically, there's a number of studies already published. Amy, that also presented earlier on, actually also have a very nice paper using metagenomic and the wastewater concept. So basically, that's of course also a consideration to use a sewage water matrix, manure or animal feces, and apply metagenomics. We have to bear in mind that this is a complex sample, and there are still limitations in the technology, especially bridging between the pathogen and the antibiotic resistant genes and mutations. But again, this is likely a technology that can be used in a future concept. Next slide, please. So my take-home message for today is that I think that we are ready. I think that better start now than being delayed or maybe never ever start. I think that we could improve the preparedness by asking ourselves the question what, where, and how. So basically, what constitutes the risk? Where should we measure, and how should it be measured? I think this is vital to take that decision as soon as possible. And then, of course, to set up the surveillance in the food production environment. And it might actually be worth, as I indicated, to think about and consider the tripart study concept with the tricycle. At least it's, in my opinion, a study that has shown its worth. It's shown that this is feasible to collect isolates, apply single whole genome sequencing, and get some tentative surveillance data out of this. Of course, also to embark on metagenomic for a future concept. Here, of course, it's important to proper harmonize and validate the concept before rolling this out on a larger scale. Next slide, please. So that was kind of my take on this. My two words are readiness and harmonization for the word cloud. Next slide, please. So just thank you for the attention, and please bear over that I'm a bit slow today because of my COVID infection. Thank you.
Thank you very much, Rene, that you were here with us, even with your COVID infection. We wish you all the best. So we go to our second speaker. That is our guest from, it's Domenico Deserio. It's our guest from DG Santé. He has worked previously as a scientific officer of EFSA, also in the area of the biohealth, and he has built up a combined experience on biological hazards, genomics, and plant pathology. At DG Santé, he has worked within the biopesticide working group on the requirements related to antimicrobial resistance of microbial plant protection products, a work which he will present now in more detail. So, Domenico, the floor is yours.
Thank you very much, Liv, and good afternoon, everyone. There's no need for this slide because I've been nicely introduced. Thank you for that. Yeah, so our activity are basically based on the Farm to Fork strategy. As you know, there are several ambitious objectives of the strategy, among others, reducing the use of chemical pesticide and improving the EU agricultural land dedicated to organic farming. So we need to foster and to chase this objective from different angles. But from the plant protection product side, our aim was to provide farmers with alternative to chemicals, so namely the biopesticide or biological plant protection products. Among several options, we decided to give priority to microorganisms, but why so? The answer is in this chart. You can see the number of low hazardous active substances which have been approved in Europe since 2009 here. And you can clearly see an increasing trend, among which the biggest chunk of biopesticide is represented by that blue bar at the bottom, which is basically representing the microorganisms. So we found out that if we wanted to foster alternatives to chemical pesticide, giving priority to biopesticide, then boosting, let's say, the access to market of more microorganisms on the renewal of those which are already approved would have been a good strategy. So we decided to do so basically by amending the existing regulations, which were quite old. In particular, the data requirements. So basically the list of data that the applicants shall provide to risk assessors first in order to take the substances to the market, and the assessment and decision-making criteria. So basically the criteria that risk assessors and risk managers shall use to evaluate this data. The existing regulation, as mentioned before, were somehow mimicking a little bit the chemical approach. So we wanted to give a new, let's say, approach to the new regulations. We have 4 amending regulations that will enter into applicability in November this year. And they are really much focused compared to the previous one to the biology and the ecology of the microorganisms. So we are trying also to really focus on the really needed data. So this to reduce also the burden for the applicants, so that in a way, for such a niche market, let's say, we can favor also and favor companies to take more microorganisms to the market. However, in the update of these regulations, of this regulatory framework, we gave particular attention also to emerging threats. And this is the link with the session with this session here on this conference today. Among the emerging threats, of course, I'm mentioning the antimicrobial resistance. We are being, in the new regulation, quite strict on the data regarding the antimicrobial resistance. And the first step of amendment was increase the clarity of our question. So in the new regulation, we really paid particular attention on asking precise questions to the applicants, so which kind of data we need. And the first step was, of course, providing clear definitions which were missing in the previous regulations. So like introducing in the legal text the concept of acquired and intrinsic antimicrobial resistance, and also focusing with introduction of the definition, focusing on what we really need to know. So not information on all the antimicrobial agents, but on those which are considered relevant, so important for human and veterinary medicine. And to do so, we introduced or we raised clarity on 2 specific separated data requirements, which I'm gonna discuss now one by one, which are always so far being, not always, sorry, but quite often confused by some of the applicants. So we receive data which are missing or data gaps, and we wanted to avoid this in the future. The first data requirement, which is really important in the new regulation, is really much specified, is the availability of treatment options. So the applicant should provide information about which treatment option can be effective against the microorganism which is meant to be in biological plant protection product. Of course, we cannot approve microorganisms which are pathogenic toward humans, but in order to protect human health, we need to take into consideration unlikely event of opportunistic infection. So the applicant shall prove that there are eventually availability of susceptibility, availability of treatment options. The second data requirement I want to present is, I think, the more important. Indeed, if the active substance, the microorganism, doesn't comply with this data requirement, it cannot be approved. So this data requirement applies to bacteria only, and it regards known functional and transferable genes which are encoding for relevant antimicrobial agents. So if the microorganism that is meant to be used in biological plant protection product carries a known gene which is functional, can be transferred, and encodes for antimicrobial agents which are used in human and veterinary medicine, it cannot be approved. And this data requirement is quite important. Indeed, 2 years ago, we also published a guidance document on antimicrobial approval and low-risk criteria linked to antimicrobial resistance, which is applicable to microorganisms that are used in plant protection. This guidance document has a stepwise approach. The first step is the employment of WGS technology in order to eventually identify genes responsible for antimicrobial resistance and check whether these genes are present in the mobile genetic elements. If genes are spotted, then the applicant is invited to perform a phenotypic testing to check whether the gene is also functional. This would provide the sufficient information to risk assessor to prove the microorganism is safe to be used. The third data requirement, which has been really well clarified and put back black on white, concerns the possible production of antimicrobial compounds by the microorganisms, which is the active substance of the plant protection product. We know that microorganisms, bacteria and fungi, they produce secondary metabolites. Some of them are even useful to us, but some of them can be harmful, can be dangerous, or can be of concern. So like toxins or eventually antimicrobial compounds. We also, in this case, we have produced a guidance document. So what we want to know is if even the manufacturing of the microorganism produce antimicrobial compounds, the risk assessor shall evaluate this possibility, because what's going to happen is that if we spray in the environment whatever has been fermented during the manufacture of the microorganism and contains antimicrobial compounds, we are going to apply like the antimicrobials in the field. So, and all the microorganisms, the other microorganisms which are naturally occurring would be subject to selection pressure, which is not nice to have. We know that the microorganism can produce antimicrobials because they do it for to compete for space and nutrients with the others. So we need to also evaluate this possibility and give the risk assessor the possibility of make this evaluation. As mentioned, we have published a guidance document 2 years ago again on the risk assessment of metabolites produced by microorganisms, still in the remit of the plant protection. I'm not going to get into the details of this table, just to give you a flavor of the fact that the guidance has 4 main stages, and let's say the novelty of these new approaches that we're not going to ask all the data to the applicants, but it's really a decision tree, like a step-by-step approach where we are really trying to reduce the request of data, especially the request of generating data. So there will be a lot of literature search required, for instance, in order to try limiting the burden for the applicant, but still not leaving data gaps here, because we need to perform the assessment. And just as I mentioned before, this applies also to toxins. Here I'm giving, of course, importance to antimicrobial compounds because of the subject of this session. Just to conclude on a couple of take-home messages of my presentation. All in all, microorganisms can be used safely in plant protection, but of course, in order to be sure that we are using them safely, they shall comply with the requirements on antimicrobial resistance, and also for improving the safety of the use of plant protection product, including microorganisms. We have updated the regulatory framework concerning taking to the market microorganisms, and the framework will enter into applicability in November this year. And I think this was my last slide. Yeah. So I'm happy to take your question if you have any. Thank you.
Thank you, Domenico, and perfect in time. Congratulations. So thank you very much. We directly move to the next speaker. She is again online. It's Professor Stineke van Houte. She is associate professor in microbiology at the University of Exeter. She heads a team studying interactions between bacteria and mobile genetic elements. Within this, she investigated new approaches to remove antimicrobial resistant genes based on the genome editing tool CRISPR-Cas. So we are all very curious to follow your talk, and the floor is yours, Stineke.
Thanks very much for this introduction. I should have already shared my, okay, so you can see my slides now, can you? Great. So thanks a lot for the introduction. I'm really pleased to be here. Thanks a lot for inviting me to speak today as well to this great session. So I'd like today to speak today about the potential of the genome editing tool CRISPR-Cas9 in combating antimicrobial resistance. So you're all aware, definitely after all the talks we've seen this afternoon, of the huge problem around antibiotic-resistant bacteria. And this problem is, of course, even more challenging because hardly any new antibiotics reach the market for various reasons. So it's clear that we need to come up with new solutions to target AMR. So one recent idea that had been proposed is the potential use of CRISPR-Cas systems as a tool to target AMR. And I think, well, all of you will have heard of CRISPR-Cas in particular because the 2020 Nobel Prize in Chemistry was awarded for the development of CRISPR-Cas9 as a method for genome editing. So CRISPR-Cas9 is such a revolution because it's highly sequence specific and it's very, very versatile, and it can be used in a wide range of organisms. And I will come back to that in the next slide. I just want to spend one slide now to tell you a bit more about what CRISPR-Cas systems do in their native context, where they provide immunity to bacteria against bacterial viruses and other genetic parasites, such as plasmids. So this immune function was discovered for the first time in 2007 in the yogurt-producing bacterium Streptococcus thermophilus. Right, so CRISPR-Cas systems in bacterial genomes typically consist of two features. So we can see the CRISPR array, and we can see a set of CRISPR-associated genes, or we call them Cas genes. And in the CRISPR array, small pieces of DNA of around 30 nucleotides in length are being stored from invading parasites, and they are being stored there, and they serve as a genetic memory of previous infection that this bacteria has seen. So this CRISPR array is transcribed and processed into small, what we call CRISPR RNAs, and people often call these guide RNAs in the field of genome editing. And these guide RNAs bind to a Cas protein complex that's formed from these Cas genes. And together, this guide RNAs and the Cas complex form a surveillance complex. And whenever this bacterium now gets infected with a phage or a plasmid that carries exactly the same sequence as the guide RNA, it will be recognized by CRISPR-Cas and the parasite will be removed. Right, so how can we use these CRISPR-Cas systems as a tool to target AMR? So the concept behind it is pretty easy. What we do is we make use of these two components of CRISPR-Cas systems, so we can use an engineered minimal CRISPR array that specifies what sort of sequence we want to target. And we combine that with Cas9, which is one of the simplest CRISPR-Cas types that we know of, and that carries out the target removal. And we've got full control on what we want to target. So we can target AMR genes, we can target virulence genes, etc. So it only needs 30 nucleotides sequence in length to determine what the target will be. So it's hugely versatile. So like I said, these guide RNA form a complex, and then depending on exactly what we target, this will lead to either death of the bacterium, for example, if we target a chromosomal gene, or it can also lead to reversal of antibiotic resistance, for example, if we target a plasmid that encodes antimicrobial resistance. So the question is, of course, how can we best deliver CRISPR-Cas to these drug-resistant target cells? And this is a major challenge. And broadly speaking, at the moment, there's two different delivery vehicles that are currently being investigated in most detail: bacteriophages and conjugative plasmids. So I guess many of you will know that bacteriophages, they are bacterial viruses. They bind to the bacterial surface. They inject their DNA, and they usually have high host specificity. So conjugative plasmids, they are circular DNA elements. They can transfer between bacteria, and they can usually have a much broader host range than phages, although that's definitely not a given. So what we can do is we can engineer these phages, and we can engineer the plasmids so that they can deliver CRISPR-Cas9 to the host cell, and then thereby they can remove the AMR target. So both methods have actually been shown in experimental work to work. So for example, these are just two examples that I've taken from literature. So phage-mediated Cas9 delivery has been successfully used in a few different in vivo models. For example, it can reduce MRSA colonization in mice, and it can also increase survival rates in wax moth larvae that are infected with EHEC bacteria. Don't worry about the details here. I just want to show you a few examples of what has been done. And conjugative delivery of CRISPR-Cas9 is also a highly efficient way of removing AMR. So these are data from my own group, but also other groups have shown that it can vastly reduce the drug resistance in both E. coli, but also in Enterococcus faecalis bacteria. Right, so it's clear that this tool can work extremely well for targeting drug resistance in a very specific manner. But what are the main areas across the different One Health domains where this tool could possibly be implemented? Well, we know that AMR spread occurs primarily between several One Health features, let's say. So in particular, from farms to the environment and to the clinic, but also between the clinic and the community, and from there to the environment. So one key opportunity for reducing AMR spread, I think, by CRISPR, lies in the animal husbandry industry. So for example, we could aim at reducing salmonella infections in chickens, infections with Streptococcus suis in pigs, or with pathogenic E. coli infections, which is a huge problem in both of those animals. And they currently require a vast amount of antibiotic treatments and cause huge losses to the industry. So CRISPR-Cas9 could potentially be administered as a food additive here. And it can, in principle, also be used outside of animals, for example, to reduce AMR levels in animal waste before it is being used as a fertilizer, for example. And that avoids, obviously, further AMR spread into food-producing environments. So I think a clear opportunity also lies in the clinic, where we could see CRISPR antimicrobials being provided either during acute infections with pathogens in either the gut or the lung or the urinary tract. But I think it could also be used in a prophylactic way. So for example, given to those patients who are scheduled to undergo surgery or to undergo a cancer treatment and are therefore more prone to future infections. And supply, possibly in the form of probiotics, is the most likely application route there. Finally, I think a more challenging, but I think very interesting possibility also lies with the potential treatment of wastewaters, whether they are from domestic or farming environments. So this would require huge scaling up of the method. But with the right delivery vehicles for CRISPR-Cas9, I think it could certainly be a possibility. And recently I saw a paper trialing wastewater cleanup in a still quite small scale experimental setting. And I think we will see more of this type of work towards this type of application in the future. Okay, so it's clear that there's lots of opportunities, and experimental work has shown the great potential of CRISPR, but we are still very far from it being used in practice. And that's because there are still really important challenges and different bottlenecks that we need to address. So I just wanted to highlight a few here. So the first one is community complexity. So what I mean with that is, the bacteria that we can target with this method never occur on their own. So they're always part of a wider microbial community. And this can make AMR removal much more challenging, for example, because the community can hugely influence how efficient CRISPR-Cas9 vehicles can spread in this community. And this is actually a work that my group is currently studying. And then secondly, evolution of resistance is a huge problem as well. So evolution of resistance can occur in the actual CRISPR targeting mechanism, but it can also occur through resistance to the delivery vehicle, so phage resistance and plasmid exclusion. So understanding what sort of resistance evolves and when it evolves is really important, and it's also one area that my group is studying. So another one is treatment delivery. So treatment delivery may not always be straightforward. So probiotics and potentially food additives, they need to be obviously safe, stable, but cost efficient as well. And if you think about treatment of waste, this requires large scale sort of reaction vessels to carry out the cleanup, and the process will take considerable time, which is costly as well. So that is a significant hurdle as well. And then finally, there are of course significant legislative hurdles to overcome around GMO issues and the use of phages, which currently still prevent these tools from being ready for the market. So hopefully I've been able to convince you that CRISPR-Cas has huge potential as a next generation antimicrobial due to its high precision and ease of use. And we could definitely harness this to reduce AMR spread across One Health domains. But we're just at the start, and key challenges need to be addressed around microbial complexity and resistance evolution. And lots of groups around the globe are actually looking at these challenges in order to move closer to an actual application of this revolutionary tool. And actually, the words here in bold are also the key words that I was asked to provide. So with that, I would like to stop my talk. I just would like to thank my lab group here, all my collaborators and funding, and of course, all of you for listening to this talk. Thank you.
Stineke, thank you very much for really a talk from which we learned, and we were really willing to listen to you. Thank you very much. For sure, we will have some questions later in the discussion. Now, I would like to introduce to our last speaker from today is Werner Ruppitsch. He's a senior scientist at AGES, the Austrian Agency for Health and Food Safety. Since 2019, he's in charge of all whole genome sequencing activities and ages. And I remember we began together in the first course on whole genome sequencing some years ago. And he's currently leader of the Horizon 2020 OEH EGP, the One Health European Joint Program project on free extracellular DNA as a source of antimicrobial resistance, and will present to us the results of his project. So thank you very much. As I told you before, to be prepared, we can do regulation, we can do surveillance, and we can do this kind of research. Thank you very much.
Thank you very much, Beatrice, for the kind introduction, and also to EFSA to invite me to present the results of this project. I have to say we just have preliminary results now, so we just started some weeks ago with the data analysis. But what we have so far, I will show you in this presentation. So we have already heard during this afternoon about the importance of antimicrobial resistance and the threat of antimicrobial resistance genes for the environment and also for public health. It's also important to know that most of the studies so far are based on analysis of total DNA, and extracellular DNA is still a neglected factor in environmental studies. The reason for this, that in general we have quite limited knowledge about the role of extracellular DNA. And the second important part is that there are also huge technical challenges when you work with extracellular DNA. So what do we know about extracellular DNA? So the definition is quite easy. So extracellular DNA is DNA and that is not enclosed in living cells. In the environment, we can then differentiate between free extracellular DNA, which is the main focus of this project. But we have also extracellular DNA that is bound to particles or also very important in biofilms. From what we know, so depending on the environmental compartment, extracellular DNA can persist in the environment quite for a long time, so 21,000 to 900,000 years. So this is quite something. The average size is between 80 and 20,000 base pair. Also important from the literature is that the abundance is quite low in comparison to the abundance of resistance genes is quite low in comparison to total DNA. So we have around 100 to 1,000 copies of resistance genes or mobile genetic elements per milliliter of wastewater. So in general, natural transformation is not very likely, but because of this long persistence and that it can persist for 900,000 years, there can be some hotspots where, of course, the probability of horizontal gene transfer can be increased. And also, as I already mentioned, it is an important structural component of bacterial biofilms. And there, of course, it's much more likely that transfer of antimicrobial resistance genes can happen. So to make it short here, a lot of factors, biotic and abiotic factors, influence the release of extracellular DNA, also the persistence and the natural transformation in the environment. So it's, from our side, really very important to have more studies and study in more detail the role of extracellular DNA and also the spread of antimicrobial resistance genes in the environment. And this is also where the project here comes in to really increase and improve the methods and the knowledge about extracellular environmental DNA. The basis of this research project are so-called open air labs. Here, a map of the Austrian open air lab. It's an agricultural area around 70 hectares in size, 100 kilometers west of Vienna. Two big farms are located in this area, and also diverse crops are cultivated in this area. We also have, I don't know if I can show. No, sorry. This was completely wrong. I don't know. We also have a small forest in this area and also a small river. So a nice environment to take the samples there. We took samples from 11 different compartments, starting with the big feces, then fertilizers, which were artificial fertilizer, and also manure from the big feces. We took samples from different soils, so fields that were cultivated with maize and winter wheat, and also treated with different fertilizers, so with either manure or artificial fertilizers, yes. And also from this forest as a comparison for a soil that was not treated with any fertilizer. In addition, we took feces from wild animals, so if available, so hunters were helpful here in collecting this feces from wild animals. We analyzed also the crops that were then used again as feed on the farms for the pigs. Some collaborators in this project also get samples from the farmers. We had drainage water from the fields. We had river water and also wastewater and groundwater that were included in this study. Open air labs we have in Estonia, in Austria, and in Portugal. And during one growing season, so starting in winter, spring, summer, and autumn, we collected around 500 samples in these different countries of Europe, and analyzed all these samples for antibiotics, pesticides, heavy metals, and then, of course, free extracellular DNA. And because we had this nice collection of samples, we also decided during the project to analyze also total DNA. And this DNA was analyzed for microbial diversity with 16S amplicon sequencing, and also resistome analysis, where we used a quite new gene enrichment approach, targeting, in principle, the CARD database. So all antimicrobial resistance targets known at the moment should be targeted with this assay that we used in this study. In addition, we isolated also clinically relevant bacterial species, also some other bacterial species from the environment, and whole genome sequenced them, searched for antimicrobial resistance genes, and did also classical susceptibility testing, and then, of course, also phylogeny. Clostridium difficile was also included in this study as a model to see transfer of isolates from pig to humans, or also from other animals to humans. And finally, all this data should be used for mathematic modeling, for risk assessment, and prediction of risk in the environment because of antimicrobial resistances. Here for Austria, we are still not finished, but these are the results for Austria for the clinically relevant bacteria. So we were able to isolate 89 isolates. Most of them were E. coli and Enterococcus faecalis. We couldn't find MRSA or Salmonella in these samples. Most samples were isolated from wildlife, so feces from wildlife and also wastewater. And we had a quite high diversity of isolates based on classical MLSD analysis. E. coli isolates carried in the mean around 50 antimicrobial resistance genes, so different resistance genes, followed by feet with also nearly 50 different genes. And 3 E. coli isolates were classified as multi-drug resistant. An interesting result was also that we found in wastewater the emerging ST1193 E. coli described from Asia at that time, and still we don't have a clinical isolate, so it was a surprise to find this clone in an environmental sample. And another interesting result from this study, from the non-clinically relevant bacteria that we found was at that time Chronobacter turicensis. So colleagues from the Veterinary University in Vienna described an outbreak where 5 hare died, and we had in hare feces 2 of these isolates. We did a comparison, though they were completely unrelated, so these animal isolates were completely unrelated, but we found a relatedness of these isolates to human isolates. And of interest that all these 7 isolates carried a new type of the MCR gene, which is conferring colistin resistance. And yeah, so it's possible from animal feces to identify the species. So hare above and roe deer, which was also living in this area below. The first results for the amplicon sequencing. So we see a high alpha diversity, except for drainage water and crops, with 16 to 1 million species-specific reads, which is quite a lot. On average, we have 90,000 species-specific reads per sample. We have a low beta diversity, so diversity from one compartment to the other is quite low, so every compartment has its specific microbiome. Exceptions here in this circle, so on the left side results for the extracellular DNA, on the right side total DNA, that soil samples, independent where they are coming from, have a very similar microbiome. Also for crops and water, we see similarities, and also interestingly for farmers and pig barns. For the extracellular DNA, we cannot see this relation farmers, pig barn, and crops water for the total DNA. For the detection of antimicrobial resistance genes based on this gene enrichment, again for Austria, so these are very also preliminary results here. We were a bit surprised. So we have the highest number of antimicrobial resistance genes in wildlife, followed by feed and manure. And the good message maybe, so the number of resistance genes in crops and river water is quite low. So finally, we generated really a huge data set that hopefully contribute to improve also the knowledge about transfer and development of resistances in microbial communities in the environment. And as we could show, we are also able with this type of studies to really identify potentially new sources of emerging resistant microorganisms along the food chain. And also, it's important to include wildlife, which is quite a neglected component in the One Health area. And we hope that our results really also have some impact on the development of future strategies as defined by the ECDC technical report on One Health. Do I have one? Okay. Some negative results, what we have learned, so not so good, but which are, in my opinion, important for future projects in this area. So what we learned is, in my opinion, we really have generated a huge data set or amount of data, but the mathematicians are still not really happy about that, so they need much more data than what we have produced here for developing really accurate models here. For the sampling in general, the 1 year growing season is, of course, too short, so this should be continued for several seasons. And then, of course, within this project, sample logistics is also really an issue to send from the different partners all these samples for analysis to the lab that is doing the final analysis. On the technical side, there are a lot of improvements necessary, starting with the extraction methods, gene enrichment, of course, and what we also learned, really ultra-deep sequencing is necessary to increase the sensitivity of the analysis. These are the partners that have contributed to this project with the external partners, also the Open Air Lab, Delft University of Technology, and RS Genetics. Thank you for your attention.
You can begin with it.
Okay, thank you. Now we have some time for each speaker a question, I think. So I would like to start with a question for Stineke. Do you have a question for Stineke?
The second one.
It's the second one. Okay. So Stineke, one question for you. And it's about the practical application of this CRISPR-Cas technology in relation to safety assessment. So you are, of course, bringing a new player in the game. And the question is, what do you think about the safety assessment of this organism that you will introduce in this environment? And what do you think, what we need to assure that we have no additional human or animal hazards introduced by this CRISPR-Cas technology system?
Right. Okay. Thanks. Thanks for that question. So yeah, that's a really good point. It's not a very easy question to answer because it all depends a little bit on what you see as introduction of foreign DNA into the bacteria that we would target. So CRISPR-Cas9 systems are obviously are present in lots of bacteria themselves. So I think that it doesn't necessarily consist of bringing in a foreign DNA, but obviously one would have to look at those safety aspects for sure. So one thing that is really interesting is that the bringing in a CRISPR system it's really simple what we bring in, right? It's just a very tiny guide RNA, and it's just that Cas9, the gene that encodes the Cas9 enzyme. So that's really simple, and then we could introduce that on vehicles that by themselves aren't genetically modified. I mean, we've got phages and plasmids that that we could use that naturally occur. But yeah, one would still have to address the safety mechanisms there. So it's quite a tricky one. And another aspect of that is, which I think is really interesting, is that CRISPR-Cas systems are themselves mobile, right? So they can get transferred between bacteria through horizontal gene transfer. So again, that might be something that we could harness towards this method as well. Just making use of the fact that these systems are already mobile themselves. I know it's not a very straightforward answer, but I hope it gives some sort of clarity.
Oh, thank you very much. I think your answer was really clear. You have the element of the CRISPR-Cas, but you have also the vehicles and the mobile elements you are introducing. So I think indeed, thank you very much, Stineke, for this answer and for being with us this afternoon, because I know you have to leave now. And thank you very much. And maybe we can give an extra applause for team.
Thanks very much. Thanks a lot for having me. It was really great. I have to pick up my kids, so I have to go. Thanks a lot. Bye-bye.
Okay, now the next question would be one for Werner, and it's in relation to the extracellular DNA. If you know what could be the relative importance for a spread of AMR or DNA, genomics or mobile genetics elements that is released in the environment originating from dead bacteria.
Yeah, as already said in my presentation, in comparison to total DNA, of course, or DNA that is intact in living cells, the concentration of extracellular DNA is quite low. So from this, the risk is in principle maybe low, but I think we also have to think in long term, as we know that about the long persistence of this extracellular DNA and also the persistence in biofilms. And thinking about bacteria and evolution, if these DNA elements are just there in the environment, depending on what happens, what bacteria need to survive, we cannot really foresee or neglect this extracellular DNA and the danger that is coming from on this side also when we still continue to create new resistances, and they are somehow then released in the environment and stay there for some time. And so I think this is the problem that we have to be aware here, that and as all the other speakers also said, we really have to try to reduce the use of antibiotics, antimicrobial resistances, and also with that, we still have maybe a problem for future generations for several years, because these resistance genes, although we are not using them anymore, are still there.
Yeah, can I continue? Because I indeed think and was really struck by your result on this wildlife.
Yeah.
Yeah. Indeed, also for the future, it's important result, I think. And related to that, have you been able to confirm this result in the wildlife also by culturing a certain indicator in this wildlife, or was it only on free DNA?
No, from all the samples, we did all these analysis, except pesticides and antibiotic residues we were not
and
analyzing.
Also,
but we were
the living cells were more?
Yes. We were also isolating bacteria from the feces from wildlife, yes. And we had, I think it was in the third position or something like that, so from these clinically relevant bacteria, we had around 33 or something like that from these 90 that we isolated. But, I mean, as shown with this Chronobacter turicensis, there are some other species also that we are not looking in that detail. Metagenomics is maybe a good way, but for this we really need deep sequencing, and I think, in my opinion, metagenomics for accurate analysis or predictions is quite not there where we would like to be with, like we have it for whole genome sequencing for single isolates, so, which is quite working and convenient and accurate, but for metagenomics, I think. And yeah, as also shown in these shortcomings, I mean, we have seen a lot of problems that we have here, so starting really with the extraction. I mean, in comparison to total DNA, we have 0.01% of extracellular DNA if we start with the same amount of sample when preparing DNA. And then there's also the risk that we lyse cells during this extraction method. So this is really a challenge.
Thank you. And a last question, Domenico, for you. And maybe you have been able already to read it on the screen here. And that's about this distinction you make between intrinsic and acquired antimicrobial resistance and the regulation. And when you read that, it's distinctive of what UCAST is using as definition of intrinsic and acquired. And maybe you can expand a bit on the reasoning behind this definition. I think it's very important aspect you have included in this regulation.
Yeah, thank you, Liv, because this gives me the chance to go in further details beyond the 10 minutes of the presentation. Yeah, it's very important for us to, it was very important for us to be clear in the regulation, so to find the good, let's say, balance between what is scientifically sound and what we need to know by the applicant. So, of course, there is some, we acknowledge that there is some difference can be some difference in some definition among the different remits in which the definitions are used. So legally speaking, of course, this definition apply only to that regulation or to that guidance document on antimicrobial resistance. And we needed really to underline the fact, still with the aim of reducing the burden for the applicants, because it's a niche market, so not so many companies would really put so much financial effort on it, and also there are a lot of small and medium enterprises working in this area of biological pesticides. So we really need to be careful that we are fostering the market properly, but in a safe way. So we really wanted to limit, let's say, the number of questions to ask to what is essential. So the first step, we identified intrinsic and acquired, because the first question was really, is the resistance intrinsic? Because we really wanted to know if this is possible to be transferred, or the resistance in your strain is held also by the other strain of the same species, which would mean that it's vertically transmitted, so it's potentially and really likely not being transmitted horizontally. So this can, as an information, can be obtained in for well-known species also from the literature. So there's a good chance that the applicant in this kind of cases is not needing to generate data, but just collect data from what's already available in the public literature. Then if there's no knowledge about this possibility of the resistance being intrinsic, then the second question would be, is then the resistance acquired? So if so, is acquired because it's transferable? Because it's not, of course, the same. So if it's acquired, it's not necessarily transferable as well. It can be acquired due to mutations, for instance. So the second question that is not intrinsic is acquired, and if it's acquired, is transferable or not? So that's where the information about the possible present in mobile genetic element is important. So that was the reasoning behind. So trying again to have, let's say, a step-by-step approach. So not to go straight into the requirement of the generation of data, but to ask the, let's say, the least possible number of questions to get to the same outcome. So the safety of the product at the end of the day.
Thank you very much.
Okay, then we have a question for Rene. No? There is no question from the audience for Rene? Rene, are you connected?
No, Rene's not connected anymore.
Ah, okay, okay. Okay, thank you. Okay, with this, we finalize this session. Now, as housekeeping genes, we have 10 minutes break, but we would ask you not to go out or just to stay very close, because these 10 minutes are needed for our rapporteurs, just to summarize the conclusions of this section. We will launch a video that takes more or less 4 or 5 minutes, and then we are here, so it's we begin in 10 minutes point, because then we go to the final session, and this session is to do a wrap-up. We know that we have several questions that have not been done, but we will have a short discussion. The chairs of each session will do the conclusions. Now I exclude me. And then we will also do some recommendations. And then I introduce the persons that will be here with us after the 10 minutes. So thank you very much. And yeah. We will have this last session as a wrap-up. And I would like to present my main rapporteur that now will do as moderator or co-moderator. And he's Jon Drelvold. He is, after almost 42 years of service as the Health Protection Agency in England, and also in the Public Health Laboratory Service before, that was the name, before he was the director of the Laboratory for Enteric Pathogens. And he was also the head of research and development of gastrointestinal infectious disease division. And he has a lot of details, but I know him as one of the major experts on AMR since many years. So thank you, Jon. For us, it's a pleasure. I think it was a decision of all the agencies that we would need someone like you to be with us. He was also a member of the Biohazard panel some years ago, and he collaborates with all the agencies when we need experts on AMR. So, Jon, the work is yours. The floor is yours.
Well, thank you, Beatrice. Is this mic working okay?
Yeah. Yes.
Well, thank you very much for the introduction. I must say, I've been working in AMR for a long time, but it has a great advantage working in AMR that people I knew 10 years ago don't look any different. So it really is a fantastic advantage. It's all very nice to see you all again, because I retired about 6 or 7 years ago, and I'm now consultant to the UK Food Standards Agency, the UK ACMSF on AMR issues. I must say I'd like to congratulate both the organisers of this, EFSA, EMA, and ECDC, for what has been a tremendous session. It's really most enjoyable. I'd particularly like to thank Beatrice and her team for a massive amount of hard work. We've been working at this night and day for the last 4 days, really, and it really has been a great pleasure. And I think we have some excellent talks today, and a lot of all the talks have been excellent, and very good responses to the questions we have made. So it really has been a pleasure to be here and to be asked to act as moderator. So thanks again. Now, I made a few very brief notes then. We've had lots of talks over this about what some data gaps. I'm sure these can be expanded on, but I just like to say what I made these notes of. First is the potential of climate change and transmission of AMR. And I think it's potentially there, but I don't think we've got full information on this as yet. The second one is the potential role of wastewater in the transmission of AMR. Once more, we do need further information of that. Potentially the new technologies, for example, the CRISPR Cas9 gene replacement therapy, which again I think has got a lot of potential, but once more, does it need more legislation? How will it be effective and so on? The role of free DNA in the AMR transmission, we've just heard an excellent presentation about this. And finally, there is definitely a lot of work to be done on new legislation regarding AMR control. And I don't envy you having to do that. It'll be quite a bit of a nightmare, but it does need to be done, and it does need to be done very quickly. I must say I was very pleased to hear Christina Greko mention the RONAFA project, because I was very involved in that. I think we reported that in 2017. I think some of the recommendations in RONAFA were very, very topical and should still be looked at, particularly in terms of maybe expanding RONAFA recommendations outside Europe to almost worldwide in attempts to actually reduce AMR. So those are my thoughts on this, and at this stage I will hand over to our chairs to maybe make their summaries of their talks, and maybe we can take discussions from there. Thank you.
Okay. I will give the floor to Domenico, but I would like to ask if any of the presents have also any questions or anything that you would like to discuss.
Indeed, yes,
from the previous
I mentioned those
session.
areas I think are key to this. I'm sure if anybody would like to add to those actual comments and make sure to add to those actual comments what I can think of key areas, I'm sure other people have other key areas they regard as very, very important. We're very pleased to hear them. So if anybody has any comments on those particular areas I mentioned, again, the potential of climate change, the potential of wastewater transmission, the role of potential role of new technologies, and the role of the free DNA in the actual AMR thing. So anybody, any comments on that? We're very, very grateful to hear them from both the audience and those remotely.
If not, I don't know if we... Yes, but I would like to ask the technicians if we can see the other speakers who are online, if they are online. We need also the two chairs. We need Barbara and Caroline. Are you there? Because we could not see you, okay? And I think also the other speakers were going to be added on the videos. If you want to put the videos on, please do it, okay? Then I think Domenico wants to say.
Since you asked about climate change, I want to share a personal reflection. I agree with what has been said and what Dr. Pruden presented, but there's one little difference, but it's an important one, that we're trying to do our best with climate change as individuals. Okay, we try not to take our car because we know that if we could take public transportation, that would be better. If we take a bicycle, well, should I travel to this conference? Maybe not. You know what? I will be online and I will make a presentation. But do we see a change? Do we see a change in the climate? No, we see nothing. Now for antibiotics, it's different because each time we take antibiotic, this modifies our own flora or that of our children. But if we decide not to take antibiotic, or the doctor decides not to prescribe antibiotic, that modification of the flora will not happen. So there's an immediate personal gain of not taking antibiotics. And that changes antibiotic risk on that individual level. So if we manage to change the behavior of all these individuals, we'll have a consequence on resistance globally. And what we see in our surveillance data is changes. It's slow, but we see the decreases. For climate change so far, despite all our individual efforts, we don't see a change. I just wanted to share that small personal reflection.
Yes, Amy, do you want to say something on that?
Excellent point, and I agree. Both challenges are extremely complex, but I'm personally very hopeful that the measures that we can take to address AMR will be more immediately measurable, and I hope that that will encourage more action. On the individual level, it's a two-edged sword, because part of the problem is the perceived benefit of immediately taking antibiotics, that people think, well, this will be of immediate benefit to me. And, you know, it's more nebulous what the broader negative effect could be to spreading it to other populations. But I think that's changing. So hopefully with education and awareness, people will realize that unnecessarily taking antibiotics does have negative health impacts.
If I could say, I thoroughly agree with your sentiments in that. And when we did the Ronifer report, we tried to make out a lot of alternatives to using antibiotics in agriculture, in the treatment of animals. We're recommending vaccinations, alternative therapies, a whole string, a whole gamut of various areas that I think should be pursued. Particularly, I know there are difficulties, legislative difficulties, and also difficulties in vaccination and so on and so forth, but this is a good point. But regarding antibiotic treatment, I've done quite a few legal cases over the last 5 or 6 years. And I find that when people have gone abroad on holiday and become unwell with gastroenteritis, they're always prescribed antibiotics. Come what may, vomiting, whatever it is, the first thing the local medics do in whatever the countries they are, give them antibiotics. When they come back to the UK or to Europe, they immediately say, stop those antibiotics. But I think there's a big gap here between, you might say, developing countries and what we're seeing in more educated countries, because those countries, they seem to just use antibiotics like sweets. This is my own personal opinion. So I do think there should be an international sort of control measures or an international awareness of this particular problem, but both in terms of humans and also animals. And also we heard a very interesting session the other day about use of antibiotics in crops. It turns out, particularly in crops, and you might say, with all respect, the Far East, they seem to use antibiotics willy-nilly in crop growing. But of course, they're not used in Europe. So there's an enormous difference in different parts of the world regarding the use of antibiotics. And I think this is an international problem which could be taken up in the various G6s, G7s, or whatever we looked at. We did have a G7 mention, I think Amy mentioned it today, which was very, very good. I think it's an overall global problem which should be looked at.
Okay. Any other question of friends? I in fact called to the stage our two speakers of the first session. We lost them, by the way, and we didn't realize.
Okay.
Okay. Yeah. From the audience, from the other speakers, do you have any other question open? Something that you would like to comment that we didn't have time? For the speakers of the section 1, would you like to comment on something that
maybe they want to
open?
comment after they heard what are my conclusions.
Okay.
Yeah, that's how I would do it. I would try to summarize what was presented, and then of course if you think that does not reflect what you had presented, then please come forward. So I think during session 1. We obviously got proof of an increasing public health concern related to the development, emergence, and spread of antimicrobial resistance, whether it's about antimicrobial resistant bacteria or antimicrobial resistance genes. We saw data from Europe, and in some cases there's a decrease or at least the halt of an increase. But then we saw for other pathogens that this is still an increase in resistance. So I think I interpret this as the result. What we're seeing is a silent, slowly evolving pandemic. And each time we take our data at ECDC with maps that go much further back than 2013, we just see this. Little by little, the maps change from green to yellow, from yellow to orange, from orange to red. So silent, slowly evolving pandemic. At ECDC, our estimates show that the majority of the infection, that is 2/3, and 75% of the burden of antimicrobial resistance is due to healthcare-associated infections with antimicrobial resistance. Not the topic of this conference, not the topic of this session. But what does that mean? That means that the remaining 25% of the burden is due to community infections, and some of them are associated with food and food-producing animals. So we heard that 8% of E. coli from UTIs in a study in the US were directly related as genetic signs that they were directly related to poultry. But what about the low and middle income countries? Well, from what we know, that's probably much higher. One issue is that we actually, there's international movement of foods, food products, and humans. So we are definitely concerned about what happened in low and middle income countries, and because of import from food from these countries, and because of international travel. So in the end, I think we need more, I concluded that we need more studies to quantify the risk posed by antimicrobial resistance in food-producing animals to antimicrobial resistance in human infections. That's one thing. And the second thing is that we almost have the whole picture, except possibly that specific from the role of food-producing animals and food. So we need more study to gather evidence on those interventions that would actually reduce all this. I don't think we need more description. We need to test interventions and be able to move forward. And some interventions may be in food-producing animals, and let's see about the effect in humans. For the second presentation, we heard about the conclusion of the scientific opinion of EFSA on the role of the environment in the emergence and spread of antimicrobial resistance through the food chain. So the conclusion is those antimicrobial resistant bacteria, antimicrobial resistant genes are present in most sources and in most sectors, but we still don't know about the dimension of the problem and its public health impact. So we're back to what I just said. We would need to measure really the contribution of food-producing animals, foods, and resistance thereof to the antimicrobial resistance in bacteria infections from humans. We also heard about specific factors that are inherent to antimicrobial resistant bacteria, for example, the formation of biofilms that are also contributing to the occurrence, the persistence of the resistant bacteria in those food-producing environments. We would need One Health-based integrated studies and ultimately surveillance systems targeting the high-priority bacteria and genes. It seems to be an agreement that we should do surveillance of genes with the new tools that are available, like whole genome sequencing, rather than the bacteria. My personal reflection is if we only do the genes, we'll do surveillance of what we know. And if we don't have phenotypic resistance, we will not identify the new genes. So we still also need the phenotypic part that will be complemented by the whole genome sequencing. And this would be essential for assessing the effectiveness of recent and future developments. But finally, we're back like for the first session. We know what to do. Obviously, prudent use of antimicrobials, paramount. Correct implementation of effective general measures like good hygiene practices, biosecurity. There's one priority intervention, which is reducing fecal contamination through wastewater treatment, reducing raw sewage discharges, and there may be a priority for plant production and aquaculture that may have been neglected in the past, but we know what to do. So I think it's the same as for the first part on public health. We know what to do. The thing is, let's do it now. And that would be my conclusion for this session.
Thank you, Domenico. I thoroughly agree with what you said. And also, remember with Robert's talk, it brought home, it reminded me of the outbreak of E. coli 104 back in 2011, which is a combination of an STEC and an enterogram E. coli. There were over 500 deaths. That strain is multi-resistant. I'm not saying the resistance contributed to the pathogenicity of the organism, but I think the resistance contributed to its spread at some stage. I think this is a very important example of how dangerous antibiotic resistance can be.
Yeah, and in that case, that is coincidence, I was working on it in Germany when we had the outbreak, and it's the first time that you could see that a resistant bacterial strain, it has an ESBL, it was an ES producer, arrived to 4,000 people that we know that had it. It's the first time that we follow an E. coli, how it was spread to 4,000 people, so it was really the spread of an ESBL apart from an strain. So it's something that happens.
Thank you. Okay, hold on.
If I can comment on different aspects that were mentioned, and coming back to E. coli and the possibility of causing infections from food-producing animals, we had already in the past several descriptions about what was called FUTI, from what could be food urinary tract infections caused by bacteria from food-producing environment, and there are some papers reporting some lineage that can be common to different animals and humans, and also there was already a big discussion about this topic that is quite complicated when sometimes you don't have a clear, let's say, clear similarity between the isolates that you are compared, as we know, because also E. coli can adapt during certain time in the gut of humans, and when they have a chance can cause an infection. So the data that Rob today talked about is important because it seems that at least they were able to see more clearly this similarity. So maybe this will be also a game changer for the ones that for a long time period has been discussing about this implication of food-producing animals on E. coli. And then we have also other aspects of the bacteria that can also be transmitted, or resistance genes that we talk about. But what right now, and it's a pity that we don't have Rene here with us, because also taking in consideration what Domenico was mentioning, right now it's time to act. But one of the points that will be important is to act with which strategy in terms of surveillance, in terms of studies. What should we consider? Should we target one bacterial species with certain mechanisms of resistance, the ones that are more emerging and on priority, or should we go to metagenomic approach? This, I think, that will be really the issues that we should consider for further discussion, and to try to start solving or stopping dissemination of different treats. And just a side comment, I think that the E. coli that is under this tripartite initiative can be used for surveying certain types of resistance, certain types of problems, but for sure this is not working for oxazolidinones resistance that we know that can emerge at the animal level, namely due to the use of phenicals. So this is just a little bit to be also to bring new possibilities of going on the direction of surveillance. And if I can, I have also just a comment regarding Domenico and the presentation that he did. And this is regarding what is planned to follow up this introduction of these microorganisms as pesticides. Because even if they don't have acquired resistance mechanism, we know that the origin of most of the resistance genes that right now are a nightmare are in the environmental bacteria, are from the environmental bacteria, so supposedly safe. There is any plan to follow up this authorization for these microorganisms to be used as pesticides, as we are at a certain point also allowing to disrupt what is the equilibrium, and we know that this can lead to some consequences. Thank you.
Thank you,
Luisa. Thank you. Can I just, Robert's got a point to make, I think, so we'd like to.
I'll try to do it short. I have one plea. I think we know enough now to act. I think we need to continue studying to get smarter, to know also where to act, but there is no reason to do more surveillance at this point. It doesn't matter if it's 9 or 9.5 or 10%. It is there. And I think one thing more is that I like really that we are sitting here together across the different sectors, because we really need to have legislation and policy that allows these, that we actually mitigate AMR crossing the systems. We have that in some countries, but even here in Europe, by far from all countries. And if we look outside of Europe, this is really a big, big issue, I think.
Thank you. Would you like to comment?
Yes, I just do.
Here? Right.
Maybe if I can follow up.
Okay.
Yes. Well, if I well understood the question, your question was about the possibility that the microbes that are used in biopesticide would maybe acquire and then furtherly transfer again. So, or acting as a donor, but after having acquired, once they are in the environment, that's what you mean? Because like if they can be approved, that's an hazard. So if they hold any gene which is functional, known, and transferable for relevant antimicrobial agent, they cannot be approved. So they are not going to be spread in the environment. So there's no risk assessment there. The answer is either yes or not. If that was your question.
So that means that even if they have, that means that if they have an intrinsic resistance gene that is not expressed, they will not be authorized.
No, if the gene is intrinsic, is then not transferable. In which cases would you consider that transferable?
Yeah, because if you go for ESBLs that are from from the bacteria from the environment, from water, for instance, Cluvera, or if you go for QNRB that are from Citrobacter also. These were really not, QNR was not really expressed on Citrobacter, and then can be mobilized and go to plasmids and causing problems.
Yeah, okay, I get what you mean. So in that case, the genetic stability of the strain is still assessed by the risk assessors. And important to say, whatever is sprayed in the environment belongs to a stock, which has to be maintained genetically stable. So what we proved to be sprayed should be genetically stable as it is assessed. So if in the moment of the assessment, the gene is not held in mobile genetic element, then we do not expect to become transferable. But there is, of course, a case-by-case assessment there. So it's not that we are dictating. We can say no when the hazard is there. When the hazard is not there, there's still risk assessment, which has to be case-by-case. So we cannot make a general rules for all the microorganisms.
Okay. If I can just react quickly to
we go to session 2, right?
Yeah, it's just to mention that the surveillance, I think that is needed in certain aspects, and namely to really identify where is the problem, because the food producing sectors are quite broad. And for instance, this problem associated with the oxazolidinone resistance is possibly only in certain types of sectors, and also possibly in certain countries. So that's the type even of surveillance that we need to really characterize where is the issue, and really take the need measures on the precise side. Thank you.
Can we move to session 2? We have the chairs on screen here. Evie's here as well, so your thoughts on from session 2 on the various points. Can you hear us?
Barbara, are you well enough to speak?
Yeah, well, I was just about to log off, and I unfortunately did test positive for COVID
Yes, we're very
last
grateful
night.
you're here. Right.
So, and it's catching up with me. I think, especially in session 2, we heard discussion about areas where we know what to do, and where we are doing things, and in particular in respect to the use of antimicrobials in animals. We are beginning to see some effects in the desired direction. So reduction of antimicrobial resistance that goes hand in hand with the reduction of use. But Junxia also reminded us in her presentation that this picture is, of course, very diverse around the world. And Dom, in his summary, pointed that out a while ago. Let's say 4 or 5 years ago, I did participate in the discussions to develop the global action plan, and in particular the needs of low and middle income countries were highlighted there, and they're not necessarily reduction in use of antimicrobials. It's more better hygiene for people, and better biosecurity for the food-producing animals, and appropriate use of antimicrobials. So I was hoping that even though the RONAFA opinion may be getting on in years, I think it really contains useful recommendations that can work outside Europe. We do have very diverse climate and food production systems in Europe. And of course, we don't cover the whole world, but I think it gives an indication of what can be done, also with little means. So I'm hoping that other people will use the report, not just people in Europe. Christina showed exactly with her analysis from existing data, showed what I just mentioned. Okay, we've done reduction of use for a long time. And maybe it's only now, 12 years after analyzing the data that are collected in the separate system, that we're beginning to see the positive effects. And I think we need to apply that patience also to other areas. Yes, climate change has been highly discussed, but have we agreed on a certain sense of direction for policies to the degree that we can actually make a change? Let's hope that we did. And with that, I would like to hand over to Christina, and definitely thank Amy and Despo for pointing out, and also Werner in the other sessions, for pointing out areas where we simply do need to know more to put in place effective policies. Thank you.
Can I take this opportunity to thank you for battling through your COVID to speak to us today? I should point out that we had a 2-hour meeting yesterday evening. I was sitting right next to you, as was on the other side. But I had some prophylactic therapy called a gin and tonic, so I'm hoping that will work. Thank you again.
Thank you, and I will log off now.
Okay, we'll turn on to Caroline now. Phil, thank you very much. Caroline there? Yes. Okay.
Yeah. Hello, thank you very much. And thanks very much to all our speakers and the organisers. So in session 2, we heard about some of the other big topics that are actually, if you like, competing with AMR in the environmental world, like climate change, like the Sustainable Development Goals. And I think, we heard how important it is to sort of think about AMR in this bigger context. Amy Pruden sort of said, think about the win-win, the synergistic wins here, where we're going to put AMR alongside these other issues and think about these difficult topics and try and find synergistic solutions, but that's difficult, and it's always like the most immediate problem is the one that will get the most attention. So actually, it's a hard slog to make sure that we can address these issues in a kind of coherent manner. And just to flag to this audience, I don't know what the background of some of the audience, but in the environmental world, AMR isn't really very well known. Okay, there's a lack of capacity. It's complicated, and it's a complicated topic, and we're really desperate for expertise coming into helping us with helping sort of practitioners and regulators understand what we need to do. I think I really understood this AMR silent pandemic. I think that bringing that understanding in is with people now with COVID will really understand that issue, and I think that's a good way to be thinking about springboarding into the environmental area. I also very much appreciated John's list of data gaps. I totally support those, and how to convert this research findings into measures which regulators and operators can use, so that wastewater treatment can be updated and so we can be as protective as possible in those sorts of measures. If I just go think about some of the other issues we picked up, so Amy sort of talked about the complicated problem. Yeah, flagged what she raised there about immediate problems get the attention, but actually we really need to understand the bigger picture. And I have to say, in Europe, a lot of the attention has been placed on the Green Deal, the European Green Deal, and thinking there's a real focus on trying to find solutions that help us with the circular economy, help us improve, reduce the impact on biodiversity of our current behaviour, help us towards zero pollution. And AMR would fit really well in this picture and this timing. So we need to really think about how we can integrate this sort of issue into that thinking. Dr. Despo Fatta-Kassinos talked about wastewater reuse and flagged that the reuse is increasing. This is part of our circular economy. It's part of our adaptation to climate change. In Cyprus, where Dr. Fatta-Kassinos comes from, is one of the major reusers of water in Europe. We heard that while wastewater treatment is crucial for reducing microbial load, we're still getting many ARGs in the sludge and wastewater. And as we're developing a circular economy, we want to reuse these resources. It's not like we can't just go treat wastewater, and put it through a pipe and think, oh, it's done now, the wastewater management's done. It's all part of a cycle, and we're going more to be reusing resources like this, and it's part of the Europe solution to some of the challenges around sustainability. And so we really need to integrate the AMR understanding into that activity. I think I'll leave it there. I know people have got lots of things to ask about, so I'll leave it there, but thanks very much.
Many thanks, thank you. Have you any further comments to add to this?
About the wastewater, yes, maybe that indeed. I think it's very important, also related to session 3, where we speak about monitoring and surveillance, that indeed the plans are at the moment not much involved in these surveillance projects. We monitor humans, we monitor animals, but I think the plans when you have this climate change, the flooding, it's always coming back to the plants. We know that plants are irrigated with the water, and we know that these plants can take up and the residues of antimicrobials and the bacteria, maybe also the free DNA, that I don't know, but surely the living bacteria, they can multiply within the plants, they translocate to the edible parts of the plants. So I think so we are eating them directly. And therefore I was so happy also with this regulation on this plant protection products, that is the starting point, I think, to bring the plants in the picture of this antimicrobial resistance, and to bring that directly in contact with water and with all the environment.
Thank you. That's very important points. Thanks very much.
Yeah.
Werner, would you have any comments at all?
well, from my point of view, so going into this field for...
It's not working, I think.
Okay, thank you. I mean, for me, it was a surprise when starting with this research on extracellular DNA. I was 2 years ago or 2.5 years ago, I was not really aware that this is existing. And I mean, still searching in the literature, there is not much about that, but I think this is an issue. And as you said, we were investigating an area that is quite a traditional farming in Austria. If we go to the more intensive vegetable production area, the picture is maybe completely different, where irrigation from river water happens. So there the situation and the risk is maybe much higher, and we have a different picture in general, not only free DNA in general, the level of antimicrobial resistances there is much higher. And I mean, at least for Austria, I can say we don't have any data for this. So I think there's a lot to do in this field, really, in this direction, to get an overview about the risk that is coming from plants that we are eating.
Thank you. I think actually what you just said, there's a question on the screen a few minutes ago, which I think you answered all the questions the person on the screen asked. So we can maybe turn to session 3 now, to just some final comments from...
Yes, I just would like to thank the speakers of number 2 that are still connected, because we are really running a lot of time. So I would like to thank you. We don't have questions for your comments unless you have something really important, but if not, we really move to session 3. We do the conclusions and then we end the session. So, okay, then we go to session 3.
I think I can be quite short because a lot of items were already said. I have as key message the surveillance, the monitoring. It's clear. As a key message from session 3 to include also other samples than we include now in our monitoring program. I talked already about the plants, but we heard also about the wildlife. We heard about the decision if we have to take the free DNA in our sampling programs, yes or no. Maybe I would think that it's not so urgent at the moment in the general surveillance programs, but maybe like in biofilms, more punctually in the certain food producing systems. We heard also do we need to concentrate on specific organisms, the priority bacteria, the priority antimicrobial resistance? Can we go with some indicators? So can we go with the metagenomics? So still some research data gaps to be filled in. I spent already some words on the plant protection regulation. So we see it's a nice example that indeed antimicrobial resistance is coming in the regulation and in the regulated products. That's, I think, a very important evolution which can help for the future. And then the last one is these new techniques like this CRISPR-Cas that we heard of. But I think we still need some further developments there also on the safety aspects and the regulatory aspects. So, but maybe it can have, maybe also for patients, some benefits. That's for the future, I think.
Thank you.
So from my side also?
Yes, from my side is just one word. When I think on the priority bacteria, I'm also involved in the data from the monitoring, and we also always look to Salmonella, E. coli. But in our sector, we don't know, or only very few, about Acinetobacter, about Klebsiella. So we don't look for it. So we really don't know if you could have a problem in humans, not only because of nosocomial infections or whatever, if we are also contributing. I mean, I say I am thinking on the environments in this food producing, in the plants, in the things that we eat raw. We don't know anything there, or very few. So thinking in the future could be also some targets there. From my side, is also okay.
I've got about 14 different recommendations written down, so it's a bit long to read them all out now, but I think everything that's just been said is actually in these recommendations, hopefully. So I don't know the situations whether we can circulate them afterwards, or do you want them written down now, or what would you like to do? The recommendations.
You can please take.
Pardon? Do you want me to say what they are?
Yes.
Okay, I'll read them up.
Yeah, or too many. You can
There's
just give 4 key points, and then.
I think the most important key point is that we've done a lot of talking. A proactive approach is really needed now, as what Robert said, what Dominic said. It's time really to actually action some of the various findings we have. Surveillance is well and good. We've got a lot of information. The key aspect is really to implement some of the recommendations now and move on that. Dominic said it's a silent epidemic and it does need controlling, so as soon as we get this under control, the better. I'll hand this over to now to Bear to finish off.
Okay, I think with this we are coming really to the end, but I would like the technicians to put the final slide on the screen, if it's possible. Yes, it's slide number 12, I think. So we see it only in this screen, but we would like to see it in the back screen, if possible. Yes. So, as we saw in most of the talks, I asked the speakers, apart from giving some questions and answers for a poll that we could not implement because we didn't have time, but all of these are some of the keywords that you have said in your talks. And the reason to ask them was, okay, they didn't understand at the beginning what I wanted to, but I say, okay, if someone listened to your talk, what would you think on? Tell me 2 words or very short. And I tried to put them together in I could not do a word cloud, but I tried to put them together in the way further, in AMR and One Health, in the agri-food culture to tackle this silent pandemic and in the environment. We have several problems. We have ARBs, ARGs, AMU, AMR residues, we have stressors, we have mobile genetic elements, free X DNA. Okay, we have a problem that is really the complexity. What can we do? We need to be readiness. We have to select priorities for interventions that you have already told some of them. We need some synergistic actions. We also need surveillance and harmonization because we need to compare, so it's very important. We need to reduce the use. We need to think that resistance is also associated to development and sustainable development goals. We need to have integrated studies. We need to refine the One Health approach. We need research. You also said we need safety requirements. And we can have perhaps high precision aims together with all the mitigations that we have. And with this, I would like to call here to the stage also the other 3 rapporteurs that are Matteo Innocenti from EFSA, Zoltan Kunzagi from EMA, and Renata Leuschner also from EFSA, that together with John already prepared all the conclusions, recommendations, and everything in advance. And I don't want to forget Bianca, that has been our supporter with all the emails to everybody that was losing the flight or with the COVID. And sorry, Bianca, because we had a script how you move and what you say, but this script was changed 20 times. So thank you also to the technicians, because I really, they were crazy with this talk. Thank you very much. And Pilar, take a picture. Thank you all. With this, we close, and I hope you enjoy it.
Thank you.
Photo, photo, photo.
You want a photo?
I want a photo.